Recording and start the session. All right, so we're going to start with our last quiz, and from there we'll take it forward. The assignment submission deadline for assignment 5 will be updated soon, so don't worry. Is there any topic you guys would like to check on before we move?
You mean to quiz or other than quiz?
Other than quiz.
Yeah, I wanted to understand the difference. I mean, what is the real benefit we get using group normalization or the layer normalization? Because that is not very clear to me.
Yes, so for that we'll need to understand the NLP side of things. So there's one difference when we do our convolutions and when we are going to talk about the NLP side of things. And the main difference is linked to the time domain. When we work with images, we don't have time domain. We only have the spatial domain, right? We have send one image only. But
Yeah.
in case of text, we have the time domain also. And we send all of the bunch of, let's say, 100 text together. So there we need to understand what happened in the last word and last word and last word. That's why we have this group normalization and layer normalization stuff where we are only interested in normalizing things between my specific image or my specific text.
Okay.
So we need to go slightly deeper into that. So today, be open on discussing anything which you might think you might want to discuss. So let's start with the quiz, but as any other question comes along, I'll just let me know. Okay, so let's start with the first question. Select all that are true. Image normalization and image equalization are same things. It's not. We discussed this also, and we discussed this, right?
Yeah. Yeah.
Cool. Okay, now image normalization and standardization are the same thing. That's also not true. Standardization is basically pushing the data between 0 and 1. Then after, so in DNN image normalization,
I
in
think this is wrong. This one.
no, I think the comma is missing. In DNN, deep neural networks, comma, image normalization means standardization and normalization. And the answer is correct. When we do normalization, talk about normalization in deep neural networks, we need to do standardization, and the way we do that is by using just that two tensor.
Okay.
Okay. After data normalization, original data cannot be recovered. Why is this not true?
After data normalization, original data, uh, only in the equalization and other things you cannot recover.
Correct. So here we can recover that because we have the normalization value, and using that we can just recover our data back. Now, batch normalization, I understand we use LR scheduler. Okay, we'll discuss LR scheduler also. In DNN machine learning, model trained with unnormalized data will take longer time to converge or may not converge at all.
Yeah, this is correct.
Right?
Because yeah, that's the whole purpose of normalization.
Correct. So keep that in mind. Batch normalization fixes internal covariate shift.
This one
Yeah,
I did not understand why it is not correct.
yeah,
Yeah,
So as I covered in the last session also, this is the paper, batch normalization, which says that batch normalization fixes internal covariate shift. But then new papers came out and they said that it does not. All it does is to keep the loss and the gradient to a limited extent compared to just pushing it across the board. So what I'll do is I'll mark it correct. Give everyone full credit for this question. A big question that really. Okay, cool.
No, so Rohan, actually, this is not about whether this question is correct or not, but if suppose we have to explain about what is batch normalization.
No, so
Is,
okay.
is it correct to say it fixes the internal covariate shifts, or we should say no?
So this is my understanding as well, and I believe that this is the correct answer.
Okay.
That's why I changed it.
Okay.
But the problem is that the way the new papers are, they claim that no, that's not true. That's why I mark it incorrect, and then correct that and I do it in all the quizzes. So this is a normal.
Sure. No problem.
Okay. Now, group normalization help in smoothing loss variation, hence helping in faster conversions. So that's true for all the normalization, group or layer or normal. Group normalization has better regulation characteristic than regular batch normalization because it introduces higher degree of stochasticity while training. Now, do you have any idea on this?
No.
Okay, so now this is, see, I'll leave it correct, but this is where the NLP part is coming in. So we need to keep the NLP in context. So just for our reference as well. I forgot all the answers.
So what is the meaning of this sentence? I did not understand. I just marked it just by taking a chance. I did not know whether it is correct or not. But what is the meaning of this line saying that it introduces higher degree of stochasticity?
Okay, so what is group normalization? Like in
Yeah.
batch, we take a channel of all the batches. In layer, we take all the channels of the current layer. In group, what do we do?
So we divide it. So we take one image and we take few channels of that layer.
We
The
don't
group.
take all, we don't take
We,
all the channels, right?
yeah. Yeah.
Yes. Now, because we're taking few channels and not all the channels, what we are saying is that it is going to introduce a high degree of stochasticity while training. So it's going to take we are taking randomly the first sequence, right? We are not going to change that. So in that, you may not have coverage of all the possible channels, which is only 50% now. That means the variation of the intensity is going to be pretty big. What you need to focus on is this particular word, stochasticity. Basically, group normalization is going to add a bit of more randomness into that normalization process compared to non-group normalization. How do we think about this? If you have a lot of samples which are close to each other and we take an average of it, that average value will be lesser than picking few samples and then taking the average value of them.
Okay. Average value of lot of samples versus average value of less samples. You're saying.
Yes.
Yeah. Okay.
And average value of less samples will keep on changing a lot compared to a lot of samples, right? Because it will randomly sometimes have a higher
Yeah.
average, sometimes have
Yeah.
and this is taken from the research paper. So if you look at the paper, that's what they mentioned. That's why group normalization is a thing. But as we discussed, group normalization is not used anymore. People prefer layer or batch normalization directly because it's simpler to implement.
Okay, so you are saying that if I take all the channels together versus if I break these channels, then there are chances that I may have only higher values in one set and the lower values in another set, or
Correct.
the distribution can be anything.
Correct.
But when we take everything, then you have just a single a single answer. So
Correct.
that,
So yeah. So today's session is on advanced concepts, and we'll cover a bit of image augmentation as well today. Now, when we cover image augmentation, I'll come back to this point, and I'll prove to you that any image augmentation technique and batch normalization and dropout and any other stuff which is not an image augmentation technique are actually the same thing. It's very interesting to think of all the process like that, but we'll discuss when we discuss the image augmentation today. Okay, now batch normalization, group normalization, layer normalization reduces our pain with respect to finding right hyperparameter. This is sort of a breakthrough because of which we do not have to spend a lot of time in figuring out what is the loss, what is the training parameter we have to pick, what is the, for example, alphas and betas and loss function we have to pick. So it reduces a lot of problem there, or where exactly we have to add dropout. As I shared with you, we are going to add everywhere. But no, earlier it was a big problem to figure out the right values of LR, right value for let's say the bias or even initialization also. There were a lot of papers between 2012 to 2016 which spoke about how do we actually initialize a neural network. It was all random, but even in that case, there was a better random approach compared to other. And all of that has sort of disappeared after the batch normalization introduction. Now, in layer batch normalization, we take mean across all, say, L7 layers in all images of the batch. That's not correct, right?
yeah.
We don't look at the batch there. Now, biases do not get subtracted out in layer normalization. We discussed that. They do get subtracted. So it's actually, in fact, I think I would have mentioned about this paper. It's called cramming bird, and I think showed you earlier also that these guys are trying to train the whole neural network in as less data as possible. Now Control F, bias. We can further drop all decoder biases with decoder bias, without decoder bias. So they've tested out a lot with and without, and what they figured out is like if you disable biases, it actually doesn't make a lot of sense, and especially when you're using normalization and other stuff, right? And they add a lot of parameters, especially in the fully connected layers. So keep that in mind. They are not helpful at all unless you've forgotten normalization in some place, which makes your network not really good. So keep that in mind and then then just remove biases, don't add them. Bias normalization can be added after non-linearity as well. That's not true. Why is this not true?
Can be added after we do it like after ReLU we add batch normalization just to make sure that all the positives are not always carried out and we get a
Correct.
negatives.
So there is no problem of adding it before or after one and the same thing. Batch normalization is dead, definitely not dead. Group normalization will always add more parameters when compared to layer normalization. Now, someone had a personal comment on this as well, but what do you think?
No, actually I worked on that assignment and I found that group normalization was not adding more parameters. It was
Yeah,
in
even
fact
for me.
equal to the
Yeah.
batch, but layer normalization was adding lot of parameters. From 9,000, I went to some 60,000.
No, but we are comparing group versus layer.
Yeah, yeah. So group was same as batch, which was 9,000 only. But when I added the layer normalization, it became like 66,000.
Yeah, for me also, when I had in
Yeah.
batch or group normalization, it was like 7,600 something, which sort up to like 53,000.
Yeah, because it is acting like as if you have added a full convolution layer itself. I can actually share the. I don't know whether I use the correct syntax or not, but that is what happened with me. I'll just share the syntax.
Yeah, same thing happened here as well because group normalization was taking shape parameters additionally as input in torch, and thus for all group layers, new parameters got added. But for layer normalization, sorry, for group parameters, every group normalization, everything remained the same. For layer normalization, number of parameters increase if you follow the syntax.
Okay, let's look at this. Right, so the probably some. I'll look at share. Is there a code? Just comment there. I'll think about that. Why that is happening. But if I think about what is happening here, for each of the blue thing, we need something. Right, we need a mu and sigma, and then alpha and beta. So every time you see one blue block, we're adding 4 parameters. Now, in case of layer and group, if you can compare just these two, if you compare just the layer and the group, then in case of group, we should have double the number of parameters compared to layer. I'm not sure why we're getting more parameters.
But in layer norm, we have this size also coming into picture, so that will make an effect.
Yeah, so I have actually posted the syntax which I am using, and that adds a lot of parameters, like 28 into 24 into 24. It will add that kind of parameters. But in the group normalization, it is just the number of groups into 28.
I'm hoping we are using correct syntax. I don't know.
Yeah,
Yes.
that's just one confusion there.
Just one point. So in layer normalization, I added this element wise affine to false so that it was not generating a lot of parameters. So that's what I did for training the model because yeah, it was shooting up to 66K parameters. So that's what I did.
Yeah, because if you see element-wise affine Boolean value, when set to true, this module has learnable per element affine parameter initialized to ones and zeros. So this needs to be false.
Okay, maybe I will try with that. False.
But Rohan, one quick question. So in
I use group norm for the layer normalization. Like there was one syntax in group norm. Like we can use for we can use group norm for also layer normalization. If you can go on the group normalization page, you can see.
I think group norm when it is equal to n.
Yeah,
the
yeah.
same
The number of
voltage is
channels
this
equal.
layer
Yeah.
normalization. Yeah, yeah. If it is 1, it becomes instance normalization. If it is n, it becomes layer normalization.
You can go down. Yeah, see there. See there.
Correct.
but Rohan, one question here. If we'll put affine to true, right? I tried that true false, but
False.
group normalization was Sorry.
Where, sorry?
Yeah. I was asking that if we'll put affine to true or false, right? It's not generating parameters, so that was confusing. That it should at least generate parameters if I'll put affine to true, right? But it was not generating that many parameters compared to
See,
layer.
I,
So
frankly, I've never used group norm, so I'll not be able to answer that question. But I have used layer norm, and I don't see that exponential increase because there's something I keep in control, and I always use batch normalization. And theoretically, we should see double the number of parameters compared to layer norm. So question was more on the theoretical side, but I'll dig deeper into why this is happening.
Yeah.
Come back with the proper answer.
Yeah, other observation was that for batch normalization and group normalization got the same number of parameters. So that shouldn't have been true as well, right?
It can be true for a specific combination of C, H, and W.
Yeah.
So
Yeah,
you can make that true, but it should not be true all in all.
Yeah, that's what I'm thinking. Our assignment couldn't have been so perfect that it was true. We didn't do any specific tuning to make it same, but got the same number of parameters for batch and group normalization. Maybe
Fair.
we're implementing it correctly. I don't know.
Yeah, I'll mark a note for myself and I'll cover this in the next session. All right, next question. So image normalization helps the model to handle different variation of images, train the model faster to handle image covariate shift, right? Something we discussed as well. Now, in case of batch normalization, it solves the intent covariate shift. Again, correct answer. Reduces need to get highly tuned hyperparameters, helps in training the deeper networks, help train the networks faster. So this again to initiate that discussion that this is actually true, and even the new paper have said the same thing in a slightly different way. Okay, a layer has 32 channels. It will have 32 mean, 32 variances for BN, one mean, one variance for BN. Not true. One mean and one variance for layer normalization. Correct?
Well, no.
No, there is
Rohan,
no
I
number
had
of images or batch size.
Best
That
size is
depends on
not
number of
given.
images.
batch size,
right?
yeah, batch size.
Sorry, one by one.
The batch size for this particular problem is not given. So can we conclude on the number of means variances for LN and GN, because they will require some batch size to be given? We
What
can
is the
conclude for BN.
What is the batch size one?
Yeah, but that is not
If
mentioned.
the batch
But that
size
is-
is 1, it's not mentioned right here.
If it is one, then
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 we
it is
can.
one
then-
mean and one
then-
variance.
Yeah, then
okay. So let's fix this question. A layer has 32 channels, and batch size is, let's say, 16. Okay. Now we'll have 32 means and 32 variance for batch normalization, correct? Have one mean and one variance for batch normalization? Not true. Have one mean and one variance for layer normalization. Now how many mean and variance?
16, because every image will have one.
Correct. We should have 16 of them. Now have 8 means and 8 variance for group normalization with 8 groups.
Yes, I think so.
Wouldn't it be 4 and 4? 4 means and
Four,
variance, because you have
four variants. Yes, you have to divide. Yes, this one.
Right? This is the correct answer. This is not the correct answer. Cool. And
But
because
the question is
question itself is wrong, we'll update it to 0 and see what we have now. A layer has 32 channels, batch size 16. It will have 32 mean, 32 variants for BN, 16 mean, 16 variants for LN, 4 mean and 4 variants for GN with 8 groups. Cool.
So,
Yeah.
okay.
Are you sure on this?
no.
I think this is
No.
wrong. 8, right?
This is wrong.
No, because if you divide it into 8, so if you divide 32 channels by 8, you will get
Hold
4.
Hold on. We are going to divide each layer by 2 groups, right? So how many mean and variance we will have? 2, right?
yes.
No, 8, but so you divide, so there are 32 channels. Now you have divided by 8. So you have 4 basically group.
No, we have
8 groups.
No.
Yes.
each
8, okay, 8 groups. So every
8
group
groups
will
with
have,
4 channel.
so
Yeah.
every group will have 1
62.
mean. Yes,
Correct.
8 means. 8 means and 8.
8 into 16 would be the answer.
Correct.
I think I didn't follow that. If we have 32 channels, wouldn't it be, if you divide it by 8, that would be 4 and 4, right?
1 second.
No, actually, it is not divided by 8. It is already 8 groups.
Okay, so here you see how many groups are there?
2 groups.
2 groups, right? To the other guy who was asking the question, was that Santosh? No.
No, it was me, Tariq here.
Yeah, sure.
So I think so. You're saying for one channel, right? So you have 2 groups in that one channel. Is
2
that
groups,
how I read it?
right? Yes.
Yeah.
And now, if you go back to
Yeah.
8 groups, which means if we had 8, we can't have 8 groups here. But if we had 1, 2, 3, 4, 3 groups here, we'll have 3 means and variances, right? So each will have 2 channels basically. In our case,
Okay. So for each channel, for each group, it will have 2.
There. Now, in case here, for each group, how many channels will have?
8 groups, so that is 4 channels.
4 channels.
Rohan, will it be like when we have these 8 groups, so we will have 4 multiplied by 6, 16 batch size? Is it like 16 into 4?
What is the 16?
Yeah,
into 8.
Yeah, the batch size is coming 16. So 16 into 4, that is 64.
Correct.
Means and 64 variances when we have this.
Correct.
16 is the batch size and 8 groups.
Correct.
16 is the batch size and 8 groups. 16 into 8 wouldn't be the mean and variances.
No, because 32 channels are there, so 4 groups, 4 into 16, 16 into 4.
1 second.
8. It is mentioned as 8 groups.
Hold on 1 second. How many groups? How many channels are there?
32.
32.
Okay. How many groups are there?
8.
8.
This means how many channels are there in each group?
4.
4.
4.
If this was 64, this was 8, right? But this and this has no effect on the means and variances, right? It's the number of groups. So don't get confused.
But the batch size
Why?
also is coming into picture.
Batch size is the spread across it. You have one variance for all for one group across a batch.
No.
See, that is where it is little
Group
contradictory
normalization
because-
work as layer
Yeah,
normalization
yeah.
as
So
per my
because in
understanding.
layer, yeah, in
If
layer it
there
is
are
equal-
8 groups, then there would be 16 into 8 means and variances.
Correct.
That's what you're
8
saying.
into,
Yeah.
yeah.
because
Yeah,
for
yeah.
each image you will have it.
Okay, then my understanding is wrong. Let me add a note for myself.
I think when batch size was 1, it was easier. When we make it to 16, I think most of the things changed.
All right. Okay, so if batch normalization, group normalization, layer normalization is used, what is true? Training larger training rate can be used. Kernel values would be smaller. Any comment on the second one?
Didn't understand much. Why would kernel values be smaller? Didn't understand this aspect.
Anyone else? Can someone else explain?
Is it because everything is going to be close to zeros and towards the mean, and so the values can be smaller?
As the channels are
The goal
normalized,
of the
the
normalization
weight will be
itself
also
is to have these kernel values smaller.
Okay, so let's see this. So let's say we have our kernels which are between minus 8 and 8 value, right? Now imagine some mean and variance and other alpha betas here. Cool. Now imagine that our channels are between -1 and 1, and then imagine our means and variances. So in which case we'll have more means and variances? Where will the amplitude be higher? Anyone?
In case of 8 and plus minus 8.
In case of plus minus, it will have it higher, right? Now let's again think in one more direction. Let's say our channel values are between -8 and 8. Think about the kernel here. What kind of values the kernel would need to identify the peaks and troughs of this kind of channel? Versus we have a channel where the values are between -1 and +1. Now think about the kernel here, which will need to be have some sort of value to identify troughs and highs here. So where do you think the amplitude of the kernel values is going to be higher, in this case or in this case?
In the first case. Um, if you add a very small value, then what is the problem in the first case also? Because every value is of the same nature. So so suppose I use a scale of say -1 to 0 and put all the values in kernel, or +1 to 0, 0 to +1, and so values are kind of normalized, and then it is just the amplitude that we are playing with.
Okay, let's see. So we have -8 and then 8 and -8. Can you see a thick edge here with high amplitude?
Yeah.
Right now, let me change the value a bit. -6, 8, and -6. Okay, and I need to think about three numbers which I multiply with them, and I get a high number because I'm exactly on top of these 3 pixels, and I want to detect a particular edge. Can you suggest 3 numbers?
0, 1, 0.
Let's say we pick 0, 1, and 0. Now that's going to give us, in fact, I. Oh, I have to change the value. And I have to, yeah, good. Let me take 2 here because I want some validity there. We don't want a lot of zeros. Okay, better would be to do -0 to -1. So we get some negative value. Here also we do -2 to -1. And here we do a value between 1 and 2. Okay, so I've taken small values here and I've taken large values here, which means here also I should have taken 0 to -1. And here I should have taken 1 to 8. We're just multiplying the random value, right? So we just want to make sure that the random value is not getting multiplied by 0, because the random between will not give us those values. All right. Okay. Now, this is the first set. So let's control V this, and then this also we have some product between the channel values and our kernel values. And then we have the values here. Okay. Mm. This better. Okay, we should not have 0 here. This should also be, this should be 1, should be -1. Okay, so now we have one set of values here and we have one set of values here. What do you conclude?
Rohan, can you explain what you did just now? The initial values are the image.
Yes, so let us assume that this is one channel. This is, so the first 9 pixels, second 9 pixels, then third 9 pixels, then fourth 9 pixels, and so on. And this is our first kernel, the second kernel, the third kernel, the fourth kernel. So when we multiply our image with the kernel, we need to sum this, and that's the value we are getting. Then we multiply our image with the kernel. The sum of this is what we're expecting. So I can actually add that, insert here, and then insert here, insert here. What do you conclude? Quick.
Okay, so the next set of values are also kernel values, right? But
This is a channel value now. These are the channel values.
yeah, no. So H to J is what? Hij is
No, okay. So this is a small kernel value, a big kernel value, and these are small kernel values. So this is -1 to 0. This is 1 to 0 to 1, and this is also -1 to 0.
No, so, I mean, see, you have not applied any normalization till now. So you are just playing with the kernel values, and we are seeing that the values are coming as 82 or 37. But it doesn't conclude that applying normalization, you can have a smaller kernel. Without normalization, also you are having a smaller kernel.
No, I wanted you to just conclude on these values right now as a first step.
Okay.
When you apply smaller kernel, you get smaller values.
We apply a smaller value. We apply it. Yeah. Okay. Now let's go here, and instead of this, I want this to be 80. This should have been -1. Then this will be 80. Then this will be -80. Right? This is next layer we are talking about now. Okay, so what I wanted to observe is this is the first channel. Okay, we started with -8 to 8. That gave us something of this sort of value, right? We are applying no normalization in anywhere in the first neural network. So it's going to keep the values here because we have not applied any normalization. That means the next channel will have pretty big values. I'm just referring to these values. It goes to 160 also. I can also go to probably 160 here, looking at just the value on top. And looking at the value at top, 160 on both the side. And now we can also take around 160 here.
So yeah, so one thing that I understood is that if you are not applying normalization, since your values are keep on growing, you will end up in a very, very large values, and hence the kernel values will also keep increasing.
Yes.
But in the other case, since the values will be within say 0 to 1 or some smaller numbers, your subsequent kernel values will also be smaller only. This looks like intuitive. I'm not sure whether this is the rule. Because you will have to then use say 379 in the next, or the 14 number, or something like 11, 12 kind of numbers. While in the first case, you are using like 100, 200 kind of numbers.
Okay, I'm just thinking how else to explain this, because I think
So can we say like this, that if suppose an image has smaller numbers, we have applied some normalization and the image has ended up with a smaller number. So channel has all the numbers between say 0 to 1. Now to do the next level of say convolution, we need smaller values to dig out the information from that particular channel. Versus and that will always be true. We will not be using very high values to find out the patterns in the smaller numbers.
no, I got it. I got a good idea to explain this. And this is linked to two features, not one feature. Okay, here we are. Okay, now this is the right way to think about it. Now we have not normalized. Okay,
You can use Zorgate to explain this.
All right, so we have not normalized. Okay, and in that case, we have two features to think of. We have one feature here, and then we have one feature here. Now, this second case where we have normalized, and these are two channels, by the way, right? In the second case, we have normalized, so not normalized. And second case, we have normalized. That's going to make sure that the channels are of similar value. Right here, we do not have any control when we're not normalizing. So we'll have one kernel, which will have to be sort of dedicated to this and one kernel which need to be dedicated to this. Now, the output of this is going to go to the next kernel where the amplitudes must be similar. So for here, bigger one, we need the smaller kernel value, as you're also thinking, which can actually take it to something like this or something like this. But in this case, we'll need a bigger kernel value where it has to amplify this and make it equivalent to this channel. Are we clear on this? There are two channels. First channel, where the amplitudes are this high. And the second channel, where amplitudes are this high. This is going to be multiplied with the kernel. This is also going to be multiplied with the kernel, and that's going to give us some output value. Now, let's say that our output value is something of this side. Now, compared to this kernel should have a lower value or higher value to make sure that the output is actually similar to this guy.
Lower value.
Lower value.
Yeah.
Sir, but the
Kernel should have a low, okay.
Higher value because your amplitude is increasing in the next.
Yeah,
step.
so I multiply this by 0.5, I get this. What should I multiply this to? I get this.
It will be high, right?
1.5 or something.
Just 1.5-ish something.
Hmm.
And because we're not normalizing the channels across each other, we'll have some channels with higher amplitude and some channels with lower amplitude. So you'll see that based on this, we'll have a lot of variation in our kernel values because it has to match the amplitude in the end for all the channels. If these were actually normalized, that means that it will have one channel where amplitude is like this, second channel where amplitude is also similar, and kernel values will have a similar value here.
No, Rohan, but why they have to match the amplitude? That I did not get. Because you want to highlight certain features of a image.
No, because we want to make sure that both the kernels get the backpropagation value in a similar range.
Okay.
If this is at, let's say, 4.5, because that's the kind of application this needs, and this is at, let's say, 0.5, because that's the kind of application needs, and now we send a, let's say, backpropagation value of 10% of that, that's going to be 0.45. That's 100% of this.
Sir.
Right? Yeah. Just 1 second. And by making sure that we normalize, what's one of the best, what is one of the best, because the side effect of normalization, all the values are between 0 and 1.
Yeah.
Right. And if all the values are between 0 and 1, my kernel values need to be just between 0 and 1 to amplify, de-amplify, because anything multiplied by the 0 to 1, it's always going to keep the output channel also in the same range.
Yeah.
Right. But if my channels are between 0, say, as you saw, let's say 160, my kernel values cannot be between 0 plus and minus 1, because that's going to reduce this to a value which is very small. We always have to, this number has to be more than 1 to make sure that we are at the same or higher amplitude. 4 multiplied by 4 compared to 0.1 multiplied by 4. Or 0.1 multiplied by 0.1.
Sir, but the batch normalization is basically making your data to have mean of 0 and a standard deviation of 1, right? So the values which are in the range of 0 and 1 can also have mean of 0 and standard deviation of 1, and the values which are in the range of, like, suppose just for the sake of example, 100 and 1000, that can also have a mean of 0 and standard deviation of 1, right? So the range basically doesn't matters to have a mean of 0 and standard deviation of 1. So
No, 100
to 1000, how can it be 0?
I just wanted to say that the large values also can lead to, the mean of 0 and the standard deviation of 1.
That 1 second. That is only true if you have all the values between 1000 and 1001.
I don't think so. Standard deviation will be 1. Maybe mean can be 0, but standard deviation will not be 1 for such a large values.
So standard deviation can be less because you are just varying the values between two values, 0 to 1. So all the values are lying between that just one number.
Okay, so one second. We are spending a lot of time. Help me answer this question. All the values are between 999 and 1001. What is the standard deviation?
Between two. I mean, it's just 2 points
across. Yeah, so that's plus and minus 1. So the standard deviation here is 1, right? But the mean here is going to be 1000.
Yes.
So we cannot have a situation where the mean is 0 and the standard deviation of 1 without the values being between 0 minus plus
Correct,
minus.
because you are taking the mean, so you have to add them and subtract them or divide by the number. So you
Correct.
Okay, so let's take an example. Suppose we have a tabular data and we are dealing with the salaries of employees, let's suppose, and then we want to standardize this data. Let's suppose we are dealing with some machine learning problem, regression, or of something of that sort, and we have a column of salaries, let's suppose, and we want to standardize that column, that particular feature. Standardization means we want to have it. A mean of 0 and standard deviation of 1. So salaries may range from the employees. Salaries may range from 10,000, 25,000 to 1 lakh, 1,50,000. So does it mean that these values cannot have a mean of 0 and standard deviation of 1?
You have to subtract it from your.
One second. So Meenakshi, what you're doing right now is first you're starting with this salary. Then you're saying you're going to standardize this between 0 and 1. So you've already made your data between 0 and 1, right? Right now, if I calculate the mean of this, what's the mean of this?
It will be
So-
very high number.
So it will be across this column, yes.
Yes, that's okay. That's what you're doing, right? Now, but in the next case, you said you have first standardized that. That would mean that you have taken basically this salary and divided by the max of this value. And max. So this is 1. This is 1. And now you're calculating mean of this. So if you've done this process, then you defeated the process of this, right? This is already the standardization part where you've already done half of normalization. So what you're saying is true, right?
Rohan,
Yeah, so you see the values are are decreased. Like we are getting a larger mean. We are subtracting the mean, and then we will divide it by the standard deviation of the column A, and then we will get the values in a lower range.
In a neural network, without using batch normalization, how will you do it? What you just said, the standardization part.
Yeah, so we are converting all the images
Into
to tensor. Like when we do two tensor.
One second. So we have done 0.3. Let's say all the pixels are 0.3. Cool. My kernel values are 0.1. I'm picking a very small value, 0.1. Cool. I have 9 such multiplications to happen. Right. I have now 0.27. Correct. I will pick 9 pixels. This becomes 2.43, and I'll pick 32 channels. We're at 77.76 right now. In case of next kernel, I'll have 0.1 again. I'll look at 9 pixels, and I will pick again. Yeah, and in this case, let's say we again have 32 channels. You see how the values are exploding? The first may be correct, but the second, third, fourth, fifth, that's where we discuss batch normalization also, that we have to add layer after layer, because the first time you have done the normalization part using 2 tensor.
Okay.
Okay, now this kernel values would be smaller. Again, goes back to the same principle. If your channel values are starting from 0.1 and 1 in the first layer, then goes to 84 in the second one, goes to 2000 in the third one, goes to, let's say, something like, if you do this again, into 9 into, again, let's keep the number of channels fixed. Now we are at 6,44,000. You can see how the channel values are exploding right now.
Understood, sir.
Right now, this is where the batch normalization came in. Now the question to you guys is, and that's why this kernel values will be smaller question is, this is the value literally at the fourth layer. This is the value at the third layer. This is the value at the second layer. And then this is the value at the first layer output, right? It's not in the image. You can see that your channels are now of different amplitudes. Now to make all the channels, so feedback equivalent to all the kernels, what kind of kernel value are you expecting? The kernel values will have to be very varied, right? For the first channels, will have a higher value. And as you're going for a bigger or a later channels, the kernel values will be smaller. You see this big variation? And if my kernels are at 44 trillion kind of values in, let's say, layer number 10, the layer number 1 kernel has to be really big for everything to make sense, the back propagation to make sense.
Yep, got it.
What you need to remember is that the delta goes to the weight, but the delta comes from the channel value, right? When we calculated backpropagation, it was a change in the amplitude. It was a change in the activation.
Mhm.
Okay, if there's confusion on this, we'll ponder more on this later on.
No, sir. Now I'm clear.
Let's get this. Now, gradient flow will not diminish to zero in backpropagation. This is part clear? Can someone quickly explain why this is true?
Yeah, because we are maintaining the distribution, like we are refraining our network to have very small values.
Now, this is also subjective, and we just saw that our channel values can explode. Now, when they explode and we have different values for different channels, let's say your salary is $4.3 million. Now, if you get a salary increase of $1,000, what will you say to your boss?
Goodbye.
Goodbye, right? But so let's see. So your salary was $2 million, and now you got a grade of, let's say, $2,000 per month. You think that's really bad, right? But if you were at not 2 million but 20,000, then that sounds like a really good upgrade, right? So when we say that our back gradients diminish to zero, that in context of something else. So the channel values were so big that the values which we're getting back were very small. And now when we apply normalization, we make sure that all the channels have similar values between plus and -1, and any gradient which flows back does make sense. Okay, now any comment on this? Do you agree?
Yeah, so this is because we are doing some extra calculation of,
Correct.
Okay.
Correct. Now, channel units, pixel values would be smaller.
So this should also be correct, right? Because the values are already small, like we are entering
Yeah,
the very small values.
Correct.
we are normalizing it, so it
Correct.
should.
Okay, last question. Now, if you create a data set in such a way that our images are automatically normalized, then would we need batch normalization? Yes, because we have only fixed the problem for the first layer. But for the future layers, we need to still add BN to make sure that all the other channels are also normalized between 0 and 1. Any question on the quiz?
This is good.
No.
Thank you.
I will come back on this and explain this in a better way. Okay, let's take a quick break, and then from there we'll start. I'm still here if you have any questions.
Rohan,
There was
I
a
have a
question in the chat. If you answer that.
Anyone else not getting this? That question?
Hello, Rohan.
I wanted to ask about ELA scheduler. So it's used on the training loss, but the callbacks typically, let's say early stopping, we use on the validation loss. Is it?
Yes. Yes.
And why it is like that? Why can't we use? Why is there a segregation basically?
Because there's no guarantee that our training loss and validation loss will have similarity, right?
Mhm.
So because of that, we can't guarantee that.
Rohan, can I ask a question, or are you answering that previous question?
I've answered the previous question, but I seem to have. Okay, so let's say this is our training curve. Okay. Let me try it again further. This is our training curve. Our validation curve can be like this, where it drops at the end. Where would you like to stop? You like to stop somewhere here, right?
Mhm.
That's why we check on the validation.
Okay. And why can't we use the validation loss for ELA scheduler?
We can use validation loss for elastic scheduler.
Hmm. Okay. Okay. Thanks.
Hello, hi Ron.
Please go ahead.
Yeah, so my question was about like research, like how can one start with like going into research. Like I had some problem statements, but due to some maths, I had some problem statement, but I couldn't solve it in the time frame. Like I just wanted to know how one should start into research field, yeah, for computer vision or maybe deep learning.
Uh, you want a philosophical answer or a practical answer?
Practical one, it will be better.
Practical answer is solve the assignment.
Yeah, so this so all the assignments which you are giving us, that's one that.
Yeah, the one I am giving, solve the assignments on time, because that's the only way. Otherwise, you can read a lot, but the reading it's very similar to reading how to drive a car, right? You can read any much, doesn't matter how much you read, but it's not going to be helpful at all.
Okay. Okay.
And problems will get creative as we move forward, and as the problem become creative, you'll have to be creative from your side as well.
Yeah. Actually, I was working on defects, like defect detection, but I like I couldn't complete it.
You're working on
Defect detection.
defect detection.
Defects.
Defect detection. Okay.
Yeah.
VQI, visual quality inspection, something
Okay.
like that.
Okay.
Brown, one quick question.
Yeah.
So we are using L1 regularization, but if we use dropout, we don't need to use L1 regularization, right? Like both will act as a regularization.
No. It's okay. So how we have to think about regularization is, I think we have our session on today is a session regularization, I believe. Okay. So how you have to think about regularization is that you're a parent and you're thinking about tuitions for your child, right? What kind of tuitions will you put your child through?
Tough one.
No. What kind? Like for which subject?
Important.
How do you know which is important?
Maybe the child is not doing so good.
Right now, putting your child in a science tuition would make sure that he's really good at maths.
No. Probably.
Right, that's where the dropout and the other regulation come in. All of them are sort of solving a specific kind of problem.
Mhm.
Now, the L1 regulation is solving the problem of keeping the weights low.
Mhm.
Now, if we want to keep the weights low, that means the channel output cannot be very small. Do you realize that?
Yes, or else it will be vanishing, right? Like
It will be vanishing. That
Yeah.
means that the kernel values cannot be very small, because really the output of the channel is built from the kernel. So it's that kind of regularization. When we add a dropout, that dropout is going to basically make sure that one kernel which was very important is suddenly not functioning. It's like think of how the Indian cricket team is working right now. Can I take Virat Kohli out and still guarantee that India will win some matches?
Yes.
Right? But go back 10 years ago. If we take Sachin Tendulkar out, will India win?
Don't.
Not 10, in fact, like 15 years ago. 10 years, I think Dhoni and all had started coming
Yeah.
in. Right? So that's the way of thinking about dropout. Dropout is basically making sure that you can drop your star fielder or star batsman and still the team performs. It has to perform, because now there's no guarantee that Sachin will always be there. Someone has to come up to the game plan and make sure that we can still win the match even though other people are not there. So it's giving more chances to other people. Right? I think every one of us was thinking when Sachin was there that in a country of 1 billion people, why do we have only one Sachin Tendulkar?
Yeah.
And it was linked to the chances, right? How many of you remember Jagal Srinath or Venkatesh Prasad?
We know, but we don't remember. Like.
Yeah, Amir Sohail remembers. Yeah.
But I remember.
You remember, right? And every
Mhm.
single match they will be there. They will be playing. There's no option given to any new player who can come. And I feel that we've lost a lot of good players in that era because of the star thing, that the star has to play. If Jagat Srinath is not injured, then he has to play. That's all. Doesn't matter there's a star performer in a Ranji Trophy or somewhere else. Now, suddenly because of IPL, we have so many new players coming in that we feel confident because we've seen them, and that's what Dropout is also doing. It is allowing us to see more kind of players who can actually contribute.
Ron, also one more question about research. Hello.
Yeah.
Yeah, so like when choosing data sets for research, either it should be like large data. Like I started with large data set, but I found that like training on large data sets on a simple GPU, I think that will take much time, and affording a high-end GPU is not very feasible for now. So is it good to start with small data sets?
See, I'll strongly recommend to go for a Collab Pro kind of account, but you should make sure that you've exhausted all the other options of training, because it will be some expense, but it's good enough expense from your side.
Yeah, because I had one data set which was about around 500 GB. So I don't think so. I tried to train on Collab Pro also, but it didn't go well.
No. That's not how you do it. If you have a 500 GB data set, what will you do? Anyone else? If I have to work with Collab, what should I do?
Stream the data, take like batches.
Wrong.
So you can write a code where it will just take batches by batches from the data and don't take the entire data. And
But
that's
where is the data?
Drive? Google Drive? No.
Google
no,
Drive.
it is. But Google Drive might not give you like 500. That is an additional expense for you.
Yeah, that also I bought. Yeah.
Yeah, so you can go with AWS, host your data on AWS, and stream the data from AWS.
Yeah, that's how you
Okay.
And that's where the prefetch part will come in. Just write a small function which sees that how much data is processed, and then you can just keep on rolling.
Okay. So we need to keep data in S3, and then we can
Yes.
stream it from over there.
And that's cheap, right?
Yeah.
But
Okay.
are there any standalone like GPUs available? Rohan, are you aware of that?
There is one Jarvis AI, I think Jarvis
But
Lab. I think.
why not use AWS itself? It's not expensive.
So I'll tell you, like I have experimented with one company called Hetzner, and they have like a flat plan. You use as much as you want, and I think they charge like $10,000 a month, and they give you a GPU of 8 GB, which is little less, but it works for most of the work. But these days they are not giving any more GPU, so I am stuck with that one.
No, I think if you move to
I
AWS,
think Amazon Spot is best.
yeah, Amazon Spot is much the cheapest I've always found.
And what about the like there are GPUs like RTX 1490 which are like 24 GB of VRAM. Like, are those good?
Yeah, they are good, but the problem is that you can't scale them, and second is that you spend all the money upfront on AWS. You'll spend it as you are going to use it. So if this is a project in which you'll be done after that, you don't need it, then the investment will go waste.
Okay.
That's how you have to think. Just literally every single answer is on the Excel sheet. Open Excel sheet, write how many times you're going to train it, see how much you're going to pay on AWS, see how much you will pay for the RTX, and then take a call.
Okay, understood. Thank you.
Okay, cool. Okay, so now let's start on this session. Today's session is on advanced concepts. We cover some advanced convolutions along with image augmentation strategies as well. Now, this is a normal convolution we have seen earlier as well. We are convolving with a 3x3 on an image of size
5x5.
5x5. Our stride right now is
1.
Perfect. Okay. Now we saw the maths as well, where we will have 9 values for our kernel, and we are looking at 9 values of our image, and then we'll multiply them, and then we'll just put them in the next layer. Now here, what is the size of padding?
1.
What is the stride? 2. What is the
2.
formula for calculating the output?
Input channel.
Input channel. What should I write?
1, 2, 3, 4, 5.
5.
Minus 2 into
padding.
2 into 2. 2 into 1.
2 into 1 is stride, yeah.
Plus
Plus
kernel size by stride plus 1.
It should be 5 plus 2 minus
Yeah,
3,
5
is it
plus,
not?
yeah, 5 plus 2. Oh, anyways, does it matter? Because the precedents, they are on the same level.
The answer changes, right?
Okay.
Right, so it's 5 plus 2 into padding. That's the total image size minus size of kernel, which is 3 divided by padding. Okay, now pointwise convolution we have covered. That's 1 cross 1 convolution. We've seen that earlier. In the depth-wise convolution, which we looked at in the last session, we are going to go the whole depth, right? Depth-wise, okay, today we are going to cover depth-wise convolution. So don't think on depth-wise, just look at the point-wise. So we'll have basically one column of all the pixels becoming one column. So we'll have three 1 cross 1s here, correct?
It's basically channel reduction, right?
Channel
Just not
reduction,
using.
yeah. So, and we call it pointwise because we are multiplying pointwise. So from 28 cross 192, we're going to become 28 cross 28 cross 32. So that's 1 cross 1. We have seen that. Then we looked at the concept of channels. Here, the input has 3 channels. That means our kernels should have also 3 channels. Here we are using 2 kernels. We also call them filters. They're going to give us 4 cross 4. Now, if they're giving us 4 cross 4, what is the stride we're using right now?
So stride of 1.
Stride of 2. Yeah, stride of 2.
No.
No. Stride of 1
So
only.
stride of 1 and
One.
no padding.
Stride of 1 and no padding. That should give us 3.
Ayo.
6, 5.
Yeah, it's 3 cross 3, 1 stride, no padding. Because
Correct.
typically it reduces by 2. That's it.
Right? So you get 4 cross 4 from 6 cross 6. Fair enough. So that's the concept of channels. And then we discussed receptive fields also, that how our receptive fields increase. Every time we're looking at a pixel, it's looking at 3 pixels cross 3 pixels at the back. And those pixels might themselves have some sort of updated receptive field. Receptive field changes a lot with the jumps, and jumps is linked to the strides. And that also we covered. Now, here's an image which talks about the ImageNet top 1 accuracy versus the receptive field. And you can see as the receptive field keeps on increasing, here it goes to 3000. What is the size of ImageNet images?
224 by 220.
Huh.
So what do you think we are getting by going to 3000?
We are looking at a lot of back. I don't know.
So
We are zooming in a lot.
Is it zooming or is it just adding the extra noise around it? Because there's nothing there. It should be black outside the image.
I think multiple areas come together in the same frame. I've seen one picture about dog nose, right? Multiple noses comes in the same kernel.
So this is how our sessions will look like. This is the last day model. Right now we are on our 6th session, which was 7th session here. Because I think one of the session was, yeah, so I think we jumped one here, that's fine. Okay, so the next session is going to be advanced training concepts, the way we're going to cover LR and other learning rates. And then the 8th session for us is going to be result high receptive field. Here we'll understand why do we need to go to high receptive field. Then you go to object localization immediately, and from there the course is very different. In fact, I think the 9th session for us deviates from the older course. Even right now, our course is very different from the old one. A lot of new things have been added. So this we'll understand as we move forward. But a short answer is, moment you start going bigger than the receptive field, instead of just storing how a dog nose look like, it's going to store a lot of orientations of dog nose also in that channel. So it has a lot bigger template which it can use to actually convolve. Right now, how I wanted to think about this is, okay. So here, this one, I wanted to imagine that this is our image, all right? And this one, I wanted to imagine that this is a kernel. Are we cool?
Yes.
Okay. Now, imagine this is a receptive field, not kernel now, okay? but this is basically what kernel is looking for, right? It's cross 3, but that's the kind of stuff it's looking for. So when our kernel is exactly at the center, it's actually trying to look for a dog nose, correct? Right, and that's how it's convolving, and it's trying to see where exactly the dog nose is. It's going to move here, it's going to move here, then it's going to move here, then it's going to move here, and so on. So slowly it's actually convolving and trying to find a dog nose, correct? But imagine that our template was much bigger. How do I make it transparent? You can't make it transparent.
You can remove the color.
Yeah.
So template means our receptive field you're talking about.
Yes. Now imagine this is how big our receptive field is. That means that I will be convolving like this. So I'm going to be here, then I'll move here, then I'll move here, then I'll move here, and then I move here, right? Now let's take this guy here and draw something inside to see what might be there. See, here I might be looking at dog nose, which was in this direction. Here I might be looking at dog nose, which might be in this direction. Here I might be looking at dog nose, which might be in this direction. Here, literally something like this, and
Rohan, I'm not able to understand how you are getting different dog noses here, because it's the same image that you are trying to convolve, and
see, that's why I said that's next session.
okay,
But let's look at,
because in my head it is like the single image. It is not that there are a bunch of images.
image, no. I did not say it's an image. That's a receptive field of a kernel. What you're looking at is a receptive field of a kernel. Yeah, you see this here? Or in fact, this is a better image. You see dog ears in different shapes and sizes?
Yes.
You see the human hand with a hint of maybe arm or jeans in different shapes and sizes. Now that's the kernel. This is what the kernel is looking for, because the receptive field is much more than the image now. So now you'll be able to find one of the, or look at this remote control or the dashboard. Now we'll be able to match one part of this big receptive field with something which is there on the image. So you get to explore a lot. One kernel now can have much bigger receptive field and can have multiple patterns inside its own recognition system. Or look at this label, for example. This is a book label.
So actually confusion is that how are you getting these many patterns? Because I am looking at one particular pattern using my kernel, and so that kernel is learning that pattern. Now from where?
Tell me one thing. Okay, continue your question first.
So from where is he getting the different kind of orientation of those patterns? Because those are like different images altogether.
What is a kernel visualization?
Kernel. So basically, what kind of features is it looking for?
Correct. So do you need an image to find what is kernel looking for after network is trained?
No, it's like a template that it is trying to match with the given input set.
Correct. Now, but if I want to see what kernel is visualizing, what is it that I'm going to do? How is that image created?
You are going to take the intermediate
based on the training images.
No. I have a trained model. I'm just going to give you the model. I'll not even tell you what data set it was created on. What will you do now? How will you create a visualization for a kernel number 47 in layer number 16?
I think I will give some image and then see how the kernel is looking at that image.
Really? There are like 100,000 classes then?
Okay. I think there is some approach. I don't remember that approach. There is some approach through which you can figure out how the kernels are looking at. I mean, that paper that you were showing is.
Yeah, so the approach is we are going to talk to that kernel and we are going to assume that the kernel has given a very high amplitude output. When will the kernel give a high amplitude output?
When it is looking at that feature that it was supposed
when
to.
It has found some feature, correct?
Yeah.
Yeah. So we are going to tell the kernel, hey kernel, you have given us this high amplitude output. Now the kernel can only give that high amplitude output if the input to that kernel was in a way in which it can create that output, correct?
Yeah.
neural networks are deterministic. So I can take the output, which is like cooked up output from my side, all ones, and then I'm going to divide by the kernel, not multiply this time, and actually get the input channel.
Okay. Okay. So you are okay. So instead of doing a multiplication, you are doing a division to figure out where
Yes.
it got.
I'm going to keep on doing this till I hit the first layer, and then from the layer, I'm going to create the image back. That's the visualization we see.
Okay. Okay.
Right now, when we do that, what we see is that for a higher receptive field kernels, we have a lot of orientations of these dogs and other feature which is trying to look at, compared to a small where it's only going to look at one or maybe two at max.
Okay.
Okay,
Sir,
so yeah.
yeah. Pardon me if this is some stupid statement or of that sort. The kernel which you showed us, it was showing the feature of just one dog or the multiple pictures or multiple images, because one data set won't have one picture, right? So we cannot have one kernel for every image. So if a kernel is trained or has learned to detect a nose, so the features will be of multiple dogs in the data set, right?
Correct. And but it has to have some sort of area to copy paste it, right? If the area
Huh.
here is only small, which is a small receptive field, then in that area, whatever it can cram, it will cram.
So that would be the reason of seeing multiple patterns, because that kernel is responsible for detecting nose, dog, nose, or nose from multiple images.
Let's say you are capable of detecting multiple errors somewhere in a code, and you have one page to write that error. If I give you a code which has 10 errors, you might be able to fill that page. If I give you a code with 4,500 errors, can you write all the errors in that one page?
No.
No, same thing happen here also. If the receptive field of a kernel is small, there's only so many variations of nodes it can add there. But
Understood,
if you
sir.
get a bigger playing field for the kernel or bigger receptive field, now it can start arranging in different patterns.
So if your data size is large, so you need to have a larger
You
receptive
need to
field.
have a larger receptive field. And as we can see now, people have started going pretty high. 1,000 up is really normal right now.
Mhm.
Okay,
Okay, thank
so here you can see that AlexNet was here, but as we have moved forward, we have started adding a lot of receptive field, and we observe a logarithmic relationship. This is also troubling, that our relationship with classification accuracy and receptive field is on log. So there's only so much we can do now. It doesn't mean that if I go to 10,000 receptive field, suddenly I'll have a higher accuracy, because you can see that we have started going on a diminishing return here. We suggest the large receptive field are necessary for high-level recognition tasks, but with diminishing rewards. For example, note how the mobile net is not shown here. But if you go to the reference, you'll find the mobile net also. Mobile net was a new network designed to work on mobile, so they were small and fast. Achieve the high recognition performance even if using a very compact architecture. With depth-wise convolution, which we're going to cover today, the receptive field is increased with a small compute footprint. In comparison, VG requires 27 times more flops than MobileNet, but produces smaller receptive field size, even if much more complex. VGG's accuracy is only slightly better than MobileNet. This suggests that network can efficiently generate large receptive field, may enjoy and enhance recognition performance. Right, so keep that in mind. You do not have to have a complex architecture to get a high receptive field. There are some shortcuts which we are going to cover today, using which you can actually get a high receptive field, and those are the convolutions which are used in mobile phones or embedded architecture. But don't assume that they're going to give you VIT or the new modern neural network kind of accuracy, because they have really a lot of parameters. Now, then we covered strides and checkerboard issue in the last few sessions, where we discussed that if we have a strided convolution, it's going to create this issue of checkerboards, because some pixels are going to be covered more than the other. And the pixel which was covered had a higher amplitude of color, then that's going to spread across more side pixels, and that gives us a problem. So the first question I want to ask you, and this is only for the new students, if you have covered this class earlier, then please don't respond. How do we get a 5x5 receptive field with one 3x3 kernel? Anyone from the new students? I can wait.
Increase the input features.
Increase the input feature. How will the receptive field change because of that?
Hmm.
Increasing the size of the channel.
But size of the channel, that doesn't increase the receptive field. That will increase the output channel size.
Add padding.
Padding will also increase the size of the output channel, not increase the receptive field. Let's look at receptive field formula. Receptive field formula is what? Receptive field.
Increasing the jump.
Receptive field old plus
Kernel -1 into jump in.
kernel -1 into jump in, which means I can't increase my receptive field now. For the later stage, I can. Right? I can't change the jump in because that's jump in, not out. So I can't, even if I increase the stride, that will not help. Kernel size I can't change because I'm saying we have 3x3. So only thing we can change is what? Receptive field input, which is also not going to change. So what can we change? The kernel size. So the question is, how do we convert a 3x3 kernel into a 5x5 kernel so my receptive field increases? And that's the concept behind this Atlas or dilated kernel. So why do we need this? First, let's look at that particular problem. Now we get a receptive field of 3x3 when we convolve by 3x3. What should we do to get a receptive field of 5x5 when we want to convolve only by 3x3? So basically a number of parameters are limited here, not the shape or size or stuff. Let's see. Now, dilated kernels increase the receptive field, that's a global view, of the network exponentially, and it has a linear parameter accretion. Basically, the number of parameters are going to be same as a 3x3. With this purpose, it finds use in application which cares more about integrating the knowledge of a broader context with less cost. Now, what exactly are these kind of problems? These problems are called dense predictions, and there are some examples of dense predictions also. The key application of dilated convolutions, authors have in mind, so this is taken from the paper, is a dense prediction where vision applications where a predicted object has similar size and structure to the input image. So look at this. Vision applications where predicted output has the similar size and structure to the input image. Can you think of some problems? What we're saying is basically the input to the neural network is, let's say, 224 cross 224. The output also happens to be 224 cross 224 or even more. What kind of problems might be there?
Maybe image enhancements.
Image enhancement is one, and one we can see on the bottom also, semantic segmentation or instance segmentation or panoptic segmentation, right? And all other problems you can think of.
Image captioning.
We can do captioning. We just need text out, right?
Okay.
Super resolution.
Super resolution. We need a higher output. Correct. More.
Visual questioning.
Visual questioning also. Okay, you want to color something, then yeah. So that's also will keep the dense output. Okay.
Neural style transfer.
Neural style transfer will also need a higher output. So in all of those cases, we can actually use dilated convolution. So let's see some examples. Now, we have something called semantic segmentation, instance segmentation, and panoptic segmentation. Now, if you try and go online and search for this, you're going to get confused on the difference on these three. So I also want to cover these three. Instance segmentation is basically just highlighting the instances, only going to get one instance output. So if you had a car here also, we'll get the color of a car. So you train your model on 10 instances of classes. So let's say we have a car, we have a dog, we have a vehicle, truck, then we have a person, then we have, let's say, house, and so on, right? So 10 classes are there. If in the image we have those 10 classes, we are going to be coloring them. And each of those instances will have a different color. So we not only identify a person, we'll identify person 1, 2, and 3. That's instance segmentation. But when we are identifying all people as one, that becomes semantic segmentation. In semantic segmentation, you will again have classes. You'll have 10 classes, let's say, and if in the image we have those 10 classes, then we are going to color all of them as 10. Now, panoptic is a mixture of these two. Now, and something else also. In panoptic, every single pixel has to be annotated. That means that if you do not have, let's say, we have 10 classes, but in the image we had 11th class, it's going to color the 11th class as a no class. It's a big deal because then you need to understand that saying no to something is also very difficult. So in panoptic segmentation, not only every single pixel is going to be classified, but it's going to be like semantic segmentation, but it will have the instance data also. Panoptic segmentation is the perfect segmentation you can imagine. Given an image, classify every single pixel as a particular class, and also tell dog 1, dog 2, dog 3, dog 4. Are we clear? If this was semantic segmentation, then all dogs will be color 1, and you may not have, let's say, a class for the clouds, and the cloud will be classified as nothing. But in case of panoptic segmentation, even though you don't have a cloud, the cloud will be classified as a no object class. So instead of 10 classes, you'll have 11 classes there.
Sir, in panoptic segmentation, there is no instant segmentation. Bounding box will not be available, right?
No, the bounding box is available. That's why you will see 3 different colors here for the person. It's just not drawn here in the image. In panoptic segmentation, you will get everything you have in semantic segmentation. You'll have everything you'll have in instance segmentation. Plus, you'll have color for a no class also, which is not in your data set.
Yeah, thank you, sir.
Ron, one question. So in instance segmentation, we are only focusing on one class and then its instances, or all class and
all classes and their instances. But it becomes difficult as we move in that direction.
Okay, then I'm confused between panoptics and instance, because in panoptics also we are doing same thing,
You
right?
see the black color here on the back?
Yes.
It is not classified as any class, right?
Mm-hmm.
If this was panoptic segmentation, that's going to color the backside saying this is a no class.
Okay. Okay.
That's
okay,
the
okay.
only confusion which most of the people will have.
Mhm.
So let's say we had 10 classes, right? So if we had 10 classes, how many class output will have in semantic segmentation for 12 objects? 10.
10.
Okay, let me write. So total objects are 12. All of them are different, for example. In case of semantic segmentation, how many outputs will have? 10.
10.
And let me make this 12 objects, and we'll have, let's say, for class B, we have 2 instances. In case of semantic segmentation, we'll just get 10 colors, correct?
Mhm.
In case of instance segmentation, we'll get what?
12.
We'll get 9 plus 2.
Plus 2.
11.
Right?
Mhm.
And in case of panoptic segmentation, what will we get?
9 plus 3.
9 plus 2 plus 1.
Plus 1, which is not of the class.
Yes. That's the difference. Okay. All right. Now, other problem is image super resolution. We are given a small image we like to enlarge. Now, this is really the part of all the mobile phones we buy these days. It comes as a operating system feature. It's there in Android. It's there in iOS, especially when you zoom in. That's what they're doing. This is called digital zoom, and a lot of AI is used there now. So this is called image super resolution. Then we have something called denoising. This is specifically used in rendering engines, especially in Blender. They have introduced this AI-driven denoising, where now you can end your this happens, by the way, because of ray tracing, because every single pixel has to be hit by a particular light ray for it to get a color, and that, you can imagine, becomes very expensive if the scene is very complex, because it has to figure out the reflections and then refractions. It has to calculate all, and then you have a parameter where you can specify how many bounces are you looking at, and the more the number of bounces, the better it is, right? Because let's say we have orange, let's say, vase kept here. The light is going to go inside that orange vase and then do multiple refractions, reflections, and then it will go and hit the wall back. But if you hit the total number of, if you have set the total number of hits to, let's say, 2, the light just goes in 1, does refraction, just stops there, right? So you have to have high number of bounces also. So this is where this problem becomes very, very complicated. You need a much better GPUs. But when you use AI, it can actually solve this kind of problem. You calculate a higher bounce rate for less number of samples and then give it to neural network, and it will solve the denoising problem for you. This also happens when your ISO rate on your mobile phones is pretty high, and this especially you would have seen at night. So to see ISO iPhone, is it not called ISO? It's called ISO, right? Yeah, ISO. Yes. So you see that when you have a higher ISO, ISO is basically how sensitive your CMOS is. CMOS is the main chip on which the light actually falls after reflecting from the lenses we have, right? And higher the ISO, lesser the light you need, which means your night photography is going to be much better. But it introduces so much noise because now it's so much, you can say, can be affected by light. So even a small issue of a light not hitting it or low light coming in, maybe it had to predict something. It has a lot of noise, and all of this problem can be solved by deep neural networks, especially in the astronomy, because we get a lot of noise. And if the ISO is low, then your image quality is good. But the problem is that the shutter has to be open for a long period of time, which means that your image is going to be blurry, because by the time the shutter closes, you would have moved already, right? So AI also solves this problem, which is also there in mobile phones. Then we have something called generative art, and with reference images, where you're sending your reference image. The left one is the reference image, and right one is the output we are getting. Something you do in Mid-Journey and Stable Diffusion kind of problems. Stable Diffusion is also going to be our last capstone project. Then we have something called key point detection, where we need a point for every single landmark on the face. This is used for face tracking. This is used for face recognition. This is used for adding some sort of, let's say, a lens or glasses or some interesting filter which you have in your Instagram on top of your image. Is this part clear? What is facial landmark tracking?
It's a lens card thing, right?
Sorry?
Lens card uses this.
Lens card use something like this, yes. They use a library called dlib, something which most of the people will use because on browser neural networks become heavy. Is the problem clear? Yes, no, maybe?
Yes, yes, yes.
Yes, sir.
Okay, also imagine that we have 64 landmarks here. I'll come to this point of 64 landmarks in some time. Okay, but remember that we have 64 landmarks here, 64 points basically. Then we have something called pose estimation. Now, I've specifically picked two different.
So, Ron, can I ask one question in the last tracking? So, is this tracking and detection? Is it like is in every frame you are kind of doing detection? That's how you track, or like there is something else going on?
Okay, what do you want to track? You just want to track the face, or you want to track how the face is moving with the lips and what is the person saying?
Yeah, I mean, okay.
I think here track is like key points tracking in each image, I guess.
That's what I'm saying. Like, is asking the face tracking. The question is, are you tracking just the face to know it's Rohan, or you're actually tracking the lips and eyes to see whether I'm blinking, I'm speaking something, or something in my mouth, or what exactly?
Okay, so that becomes more complex. Like you are trying to hear, yeah, the points. It becomes easy. Rohan's face or someone else, it doesn't matter. It just tracks that face. But if you are going to try to check something, then you have to do detection in every frame.
Yes, so that's where this comes in. This is what you use for deep fakes.
Okay.
Okay, so there's a reason I've picked this image for facial landmarks and I've picked this image for pose estimation. Generally, when you see pose estimation, you'll see one image, and in that one image, you'll have these bright spots for the joint of the arm, for the end of the arm, for the hip, for the leg, for the knee, and etc. But I've shown you 1, 2, 3, 4, 5 images here. Here, even though all the 64 points are shown as overlapping one image, you are going to get 64 different channels exactly like this, and in each of the channel, you have this landmark, which means that if you want to track 64 points on a face, your output is going to be the size of the image. Let's say 224 cross 224 cross 64. And each of the channels is responsible for tracking, let's say, the corner of the left eye, the corner of the right eye, the left corner of the left eye, the right corner of the right eye, the nose, the joint, the point between the eyes, then the forehead, then the hip, so not the hip, then there are lips, the left corner of the lip, the right corner of the lip, and so on. So how many channels are you seeing right now in the output?
64 channels.
You're seeing 64 outputs in the channel as the output. All of them are superimposed. If I superimpose all of them, 1, 2, 3, 4, 5, 6, then it's going to become something like this, right? And we can see here as pose estimation, and look at some images, and you are going to get one such image. Again, you can see 1, 2, 3, 4, 5, 6 mentioned separately here. But you will get something, and the lines are basically driven by just connecting them, and we know which lines need to connect with what. This is also here. This is a good example, right? So open image in new tab. So this is generally how it's shown. But if you can really count here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13, 14, 15, 16, 17, 18. This is 18 landmark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Would have missed 2. And then generally there are more for the face also. So because we like to know the orientation of the face. So 1, 2, 3, 4, 5 for the face. That tells us where exactly we're looking, right? So the total number of points, how many channel outputs are required to create something like this?
So one channel for one.
Right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Most of the human pose estimation will have 18 channel output. We good?
Yes, sir.
Okay, keep that in mind, because then we are not going to cover this in our course, but if you do work on it, you need to know that what exactly you're going to get. And this is how you think about every single thing you're going to track. That you have to have one channel specific for tracking that specific thing. Okay, so what is the output above? In all the cases, we saw the output is dense. The output is going to be size same as the input size. So the problem we have is convolution is rather a local operation. We get to see exactly below what we are looking at, right? We are not able to like sample from my periphery also. Improving the resolution of segmentation result, dilated convolutions, what we are going to cover now, present a potential solution for this problem. They are capable of capturing global context without reducing the resolution of the segmentation map. Normal convolution neural networks are based on the fact that each convolution layer collects information from a larger neighborhood around each pixel. This means that the upper layers of the network, each pixel in the feature map could potentially hold information about a large region in the image. We know that. However, experiments show that during the learning, this usually is not the case. Rather, the information in each pixel stays localized and the network does not live up to its full potential. So what we observe is that even though, one second.
No, I have one question regarding the previous comment that you said that each landmark position should be one channel output. How will you train a network that it will give out that particular information from that channel?
I didn't get the question.
So you said that for say post detection you need 18 channels.
You have to have the training data also, right?
So we will create the training data in such a way that each channel is giving you the output of say for example eye, it is detecting eye from the human. So the training data should be like that.
Correct.
Okay.
Someone has to sit and annotate that data.
Okay.
Okay, so this is our assumption right now, that if our kernel here has a receptive field of, let's say, 40, it is actually looking at 40 pixels in the image. But what we have seen is that effective resolution or effective receptive field does not increase linearly. It has a very good focus of this area, but this area is not generally covered very well. Why that happened is a completely different story. A long session is required just to understand that part, but it has a really good idea of what is happening exactly below it. But for the areas which are next to this focus area, it's like your eye. When you're looking at something very specific, the rest of the area around it gets blurred. That's how our neural networks also are. So this is not to say that our receptive field is not increasing. The effective receptive field is increasing, but it's not increasing linearly on both the sides. All right. Did you understand what we discussed here?
Yes, sir.
Okay. Now, however, experiments show, right? So there's no direct conclusion or one single line in which we can explain why this is happening. So in the experiments, they see that the kernels are really good at capturing features which are exactly below or in the center of the receptive field compared to the periphery. My feeling is that happens because based on the area. Let me explain it like this. Like how I think about this. What I feel is that based on the area, okay, so imagine that this is the effective receptive field of the kernel, right? Now imagine that I have some feature here in the center, and I have some feature here as well, and some feature here, and then some feature here, and then some feature here, because my receptive field is increasing. All the new experiments are on the high receptive field kernels only. Now, if I'm exactly on top of my feature, which can be the case here or the case here, I will be able to identify that. But this surrounding area, which is now in no man's zone, I will not have a good idea of what exactly I'm looking at. I can't just fill up every single pixel with just a dog nose. Otherwise, it won't make sense. And as this feature and this feature are merging, this area will have to have some sort of diffusion, some sort of, you can say, blurred area where features are there, but they're not there. Also, the amplitudes are not high because I don't want a nose to be detected by the hair of the dog, right? That has to be exactly nose. So we have a high point of feature here. We have a high point of feature here, but the area in between will not have such a high point. That's how I think about this particular problem. Here will not have a high point of feature. Okay, this should give you some sort of intuition. Okay, now dilated convolution, change the rule of the game by using a kernel of the same size as the normal convolution, but spread it over a large area of the image. And many such applications, in many such applications, one wants to integrate information from different spatial scales and balance the two properties. Local pixel level accuracy, such as precise detection of edges, can be done by only 3x3 normal convolution and integrating a knowledge of a wider global context. You've got some idea of what this can do, but what exactly look like? This is how it looks like. What is the size of the kernel right now?
3x3.
What is the receptive field of the kernel right now?
1, 2, 3.
5x5.
5x5.
So this is a shortcut. The only alternative we have is to use a 5x5 kernel, right? We don't want to do that because then my output is going to be pretty. My output is also of the same size. If I use a 5x5, 5x5, that means to use a 7x7, I have to use a 7x7. But you realize that I can use this kernel also for a 7x7 also, right? And you can also, this is sort of sampling our data. It's not actually like extracting an edge or something. It's like sort of sampling. What does this pixel belong to? What does this pixel belong to? Am I looking at the same class or not? That's the kind of thing we need in our image segmentation kind of output.
Wouldn't it cause checkerboard issue a lot?
Checkerboard issue happens when we cover one pixel more than the others. Here, that's not the case.
So if I look at the third one,
yeah. So don't look at this image because this is just a 1, 2, 3, 4, 5, 6, 7x7. Imagine a big channel, 300x300 or 100x100. There, the last two rows and last two columns will have issue as always. Even 3x3 does not cover last two rows and columns in an equal number of way, right? As we can see in the first image.
Okay. And if I try to make an analogy to NLP, is it kind of a skipgram that we are trying to do here?
Skipgram.
So it's not continuous words, it's skipping some words in between.
Yes, I believe so. I'm not using skipgram.
About the contextual information, like 5 words here and 5 words there, then what is the in between word?
Yeah, I can't comment on skipgram because I'm not use it.
No problem.
Okay.
Rohan, so why is the receptive field 5x5 here? 1 pixel is still looking at 3x3 pixels, right? I mean, by the formula it makes sense, but I mean,
no. Look at the top. This is the 1 pixel, right?
Yeah.
The first pixel looking at how many pixels?
It's looking at like 3x3, right?
No. It's looking at 9 pixels. I agree there. But what is the area from which these 9 pixels are taken from?
Yeah, that is 5x5.
That is 5x5. So receptive field is the area from which the pixels are taken from.
Okay.
This is very similar to thinking about how do we know the population of India is 1.5 billion? I don't think anyone has ever come to you and asked you that and told you that you are one of those people, right? We sample. So here also we are sampling, and it's a pretty dense sampling if you think about it. So it gives a good idea of what exactly we're looking at.
Yeah, got it.
So Rohan, like at a pixel level, the feature won't change as a pixel level. So has experiments been done? Like if we go instead of 5x5, we go to 7x7, still it gives us a pretty good result. So why like 3 to just 5? Why not like going from 3 to 7x7?
So when we are going to be using this, we are going to be using a 3x3 normal convolution plus a 3x3 dilated convolution with a dilation of 2. What you're looking at in the image right now is a dilation of 2 already, which means every single kernel you have ever used has a dilation of 1. Are we clear? I can just write this 3D1. This is a normal convolution. It is a dilation of 1. Each pixel is separated by each other with 1, basically. Everyone is next to each other. Then you'll add a this, then you'll add a 3D3. So you will have a receptive field of 3 kernel, you'll have a receptive field of 5 kernel, and then you'll have a receptive of 7 kernel working simultaneously. That will be like a group convolution.
Where these are typically used, is it earlier in the layer or later in the network?
They are used later in the network.
Why is that reason?
Initially, you want to extract some features before this starts making sense.
Okay, thanks.
When I use later, I don't even mean to say the last 30%. It's like from the first 30% might not have them. After that, you add them.
Okay.
Okay, so this is dilation of 1, your normal kernel. Dilation of 2, where we have a gap of 1. Dilation of 3, where you have a gap of 2. Okay, now this is, as I said, how you're going to be using it. This is a normal convolution on top. You have 4, 8, 16, 32, 64, 128, 256, and 215. But here, when you are going to be using our dilation, initial one you may not want to add, but after that you will add a dilation of 2 or 4 or 8 or 16. Here dilation is increasing as you're moving. You can have a group convolution where you have dilation of 1, 2, and 3 simultaneously, and then you are progressing also. This is just one example. There are many neural networks where this is used. Are we clear on this? Any question?
Yes, sir. Didn't understand why we add dilation later in the part and not in the initial part.
What is the use of dilation kernels?
We're increasing the receptive field, right?
Okay, and what do we want to do by increasing receptive field?
Getting the knowledge of wider global context.
Right, so that means you are now okay, let's say I'm looking at a very thin edge. I'm looking at something of this kind of edge. Okay, now if I have a kernel which can look here and look here and look here, how will I basically help myself? My feature should be something, right? My feature should be sort of this big for me to be able to actually use a dilated kernel and know, oh, I'm still looking at cow. Oh, I'm still looking at cow. Oh, I'm still looking at cow.
Okay.
Right, so the feature looked at or found should be big enough for the kernels to start making sense. Only then I'll get a global context of whether I'm still looking at the same feature or not. And that's how it becomes so easy to solve problems like semantic segmentation. Think of this problem. I am on that human, yes. I'm on that human, yes. And I don't need to now convolve by 3 cross 3 only. I can have dilation of 4 and then slide across it to see, yes, it was all human. All right. Okay.
Rohan?
Yeah.
So we need to apply dilation at the end of the layer. Maybe actually higher level features only you are applying the dilation concept, isn't it?
Okay. So now if you want me to quantify, we have block number 1, 2, 3, and 4. I'll start applying it from block number 3 and 4.
Yeah. Okay. Shall we start in first layer itself?
You can apply, but nothing will happen.
Yeah. Because actually. Actually first layer we are learning the lower features.
Smaller
so
features.
It will be helpful, I think so.
Yes. No, smaller features, right? Smaller features are small. They do not cross even a area where dilated kernels will make sense.
Okay. So we need to apply dilation after some layers.
Correct.
From middle level to higher level features.
Correct. Okay, another intuition to quickly think build on this. Imagine that you can only see through a microscope. That's a 3 cross 3. When would you want to not see from a microscope?
When you want a bigger picture, or
right?
When things
Right?
are clear to you.
So you get an idea, right? When would you actually want to use dilated kernel and when you don't want to use that? Dilated kernel is your eyes, normal eyes. When you are looking at 3 cross 3, that's a microscope. And when you want even bigger one, you will go for a telescope where you do not want to look at every single crater on moon. You just want to look at the moon from distance at a zoom level, but don't want to go on a crater. If you want to go on a crater, then you will increase your when you want a photo of the moon, then you're going to look from telescope. But as you are now going deeper, you're going to look at increasing the zoom level, and then you're going to start looking at the sand on the moon. That's a 3x3. When you're looking at the crater of the moon, that's probably a dilation kernel of 3. When you're looking at the full moon, that's a dilation kernel of, let's say, 7. That's the idea. Are we cool on this?
Yes, sir.
Okay. Now the next question. We saw the other. Now this is the reverse of that problem. How do we increase the channel size of the convolution? Right now, whenever we convolve, we always get a smaller size output, right? Yes, no?
We also increase the number of channels also, right?
Sorry?
We also increase the number of channels.
This is not the number of channels, this is channel size.
So you mean the output, let's say 28 convolving with 3 by 3, we get a 26 by 26.
That's what we get right now. But what if we convolve by 28 cross 28 by 3 cross 3, but I get a 32 cross 32 output?
Oh, okay.
Where will this problem be useful? When do I want the output to be bigger than the input?
Zoom out.
Super resolution?
Scaling, super resolution. Yeah.
Scaling, super resolution, and
neural style transfer.
Okay. Now there are networks called unit.
Unit, yeah.
Right. And in the unit, what we'll do is
segmentation.
Yeah. So what we do basically is that we take an image and we make them smaller as the channel size becomes small, and then we upscale it. So all these yellow guys is where you're going to see that we have to use something like this, where the output channel size is going to be bigger than the channel size. Okay. So we have a kernel size 3 cross 3. We convolve by 5 cross 5 and get a 3 cross 3. What do we do to get a 7 cross 7 or larger channel output? There's one simple approach, but it's inefficient. If you go back to the formula, in the formula, we can see the output channel size is equals to the input channel size. So let's say that's 5 plus 2 into padding. So let me keep it 0 right now. Minus the kernel size 3 and divide by stride 1. So if I increase the stride, my channel size becomes smaller. So I'm not going to increase my stride. Kernel size is not allowed to change. This 0 I can change. So if this is 1, I get into 1. Sorry, if this is 1, we get 4. If this is 2, we get 6. If this is 3, we get 8, and so on. But this is stupid, right? Because I'm going to just expand in the white area here. So I will not get anything useful. Just convolving on gray pixel doesn't give me anything, right? So this is not useful. But what we can do, we can think of what happened here, but reverse this. What if instead of expanding the kernel, I expand the channel? Are we clear?
Could you repeat that, please?
So we are dilating the input over here?
We are dilating the input over here. Instead of dilating the kernel, we dilate the input. So now my input image becomes 1, 2, 3, 4, 5, 6, 7. And I'm convolving by a 3 cross 3. So my 3 cross 3 input now becomes a 5 cross 5, as you can see. Okay.
So you are adding the gray area in between the image.
That's my next question. What is the color we are going to add in the white boxes here?
Could be average of the
pixels. There are many ways of adding it. One is adding a gray pixel all across. That doesn't make sense because that's going to create a gray checkerboard issue for us. Second would be to add the average. That's okay, but that will also add sort of a pixelated problem for us. It will also cause a checkerboard. By the way, this will always cause a checkerboard issue. So we are only talking about scale of 0 to 10. If I add gray, I'll get a checkerboard issue of 10 issue. If I add the average of 2 pixels, then I'm going to get a checkerboard issue of probably 5. Another way is something called linear interpolation. And I'm specifically mentioning this term because this is used in the quiz next time. It's called linear interpolation. And this is used in all the pinch to zoom and image scaling examples. So what we do basically is try and figure out something like this. We don't just zoom linearly, right? We'll try and figure out what should be the point based on the overall average. So you can think of it like this. In fact, it's very important. What I'm discussing right now, it's a mathematical concept, but you need to remember this. Okay, so there are 5 points we're considering: x1, x2, x3, x4, and x5. Okay, Now, if I just do x3 minus x2, what are we doing? Mathematically, this is what?
Subtraction.
Go on the integration and differentiation there.
Shifting.
This is the first derivative. Conceptually. Yes, no?
So when you subtract, you're saying it's a derivative?
I'm saying it's the derivative. Conceptually, we can think of dividing this by something also, but it's a derivative of delta 1 and delta 2.
You are subtracting very little value from something.
Yes.
That's what you're saying.
Yes. Conceptually similar to the derivative. Yes, no?
Okay.
What is derivative?
X minus delta x. What's the change in the?
That's what this is. If pixel number 4 minus pixel number 3, we do, that's the first derivative, right?
Oh, yeah.
Right. So I'm telling you, the maths is simple if you break it down like this. Otherwise, it's complex. Okay. Now this is fine. But now if I were to do this, what derivative is this?
Derivative of a derivative.
Which is a second derivative.
Second derivative. Okay.
Okay. And then we can move forward also. Okay. Now the first derivative, which is x2 minus x1, is basically the angle of the line.
Yeah, slope.
In all the cases, I'm assuming that we're dividing by 1 and we're dividing by something always. Okay. So don't worry on where's the dy or dx term on the bottom. So this gives us the angle of the line, correct?
Angle
Yes,
of
no?
slope. I mean, you're saying slope is equal to angle in this case.
Yeah. This is going to give us the slope of the line. But if I do this, what am I going to get?
You're getting the local minima here if you're doing a derivative or derivative.
This is called curvature. Okay, let's think of this immediately using an image. Now, and it's very useful, by the way, and this may never be covered for you by anyone. So just focus here. I'm not sure when you will get to solve this kind of problem, but it's very important that you understand. Okay, now imagine that I have this kind of curve. Okay. If I were to take a derivative of this, and every time I have some angle here, okay, so let me think of it like this. Can I think of this line as being 70 degree?
Yeah.
Right, and let's say this is up to 90. So for 70 degree, we are going to be somewhere here. Then here we are at some 60 degree, and then here we are at, let's say, 45 degree, right? Here suddenly we are at infinity, 0 basically. So I'm going to be here, and then I have here. So I'll have some sort of this kind of graph. So I'll have this and this kind of graph for the first derivative, correct? You can't see.
For the parabola, yeah.
You'll get this kind of graph, right? This is this point. Then this point will be this point. This point will be the 0, 1, and then so on. Cool.
Rohan, could you explain this again? I think we missed the representation diagram.
1 second. I just dropped my pen somewhere. Keep trying with my hand right now. Okay. This is easier. Okay, so imagine that we have a graph like this. Okay, and now I'm drawing the first derivative of this, and this here is 90 degree. This point is something like 70 degree for me, so I'm going to drop a point here. Then this here, let's say, is around 45 degree. So this is 90, so 45 should be somewhere here, and this is 0. and this is going to be here. So if I draw this, I'm going to get something like this. Yes, no?
You're plotting the derivatives that you
I'm just plotting a derivative.
Okay.
Okay, right?
Okay.
Okay. If I were plotting the double derivative, what is the change in angle from here to here?
You can look at the derivative graph. That might be easier, I think.
But what do you think? What do you think is the change here?
Very less.
Is
I think.
Very little, right? So what I'm going to get actually is a very little change. But here, what will happen? A steep change.
Yeah.
And then very little change. Are we clear? This is what? Derivative second order. This is what? Derivative first order. Now can you think where you can use double derivatives?
For learning algorithms
To get the
optimize it.
edges.
So that's the direction I want to start thinking on, because we are not a maths class, or we're not a math-driven course. We are, but like not in that sense. So that's why that's the kind of intuition I wanted to give you. When you're looking at the data and you want to figure out change in the data, first derivative will work for you. Just subtract the values and you're going to get a consistent value output. But when you want to figure out when the major change has happened, you need a double derivative. That's the acceleration point, right? When you subtract x2 minus x1, you're looking at speed. When you're subtracting speed from speed, you get what? Acceleration. When you, in fact, there's another something on top of this also. What happens when you subtract acceleration from acceleration?
We get
jerk.
You get jerk. You get even bigger deviation point, right? Now here, in fact, if you see that our turning point was fine, but if my curve was something like this, then here, in fact, I can get quite possible my whole thing is something like this, right? If I want to get something like this, then I have to take a third derivative, because I have to look at points which are even farther from my origin point. Are we clear?
Yeah. Can you comment on the usage of this in the work that we are doing?
Usage of the work we are doing.
Yeah, as in computer vision, how it can be used.
No, this is not a computer vision problem. This is more on a linear data which you're getting kind of problem. So where did we get this from? We get this from linear interpolation. In linear interpolation, you're going to find the point intermediate of 2 points, right? And so, okay, where did we get this from? So
these are existing interpolation methods, right? Newton-Raphson and those kind of things, right?
Yes.
Lagrangian way, and yeah.
So, Rohan, one way to think is that if you want to say do a checking on the change, how much change have we, say you are doing an anomaly detection kind of a problem, where you are trying to figure out whether the values have changed significantly or they have changed very less.
This is what I want to show you. 1 second.
Yeah.
So first, talk about the reverse problem. If your solution is like linear interpolation or a second order, then you're going to get sort of a look at a dotted line basically. That's the second order linear interpolation. If it's the first order, then you will have straight lines joining these points. We don't want that. That's the average. If you do second order, then we're going to get a curve which fits something like this. If you go third order and higher order, then you're going to get exact replication of the data which we have. But it becomes a difficult problem to solve and computationally heavy also. Similarly, if you're trying to find out change in a data, first order is just the simple straight angle average. Second order will give you a better idea. Third order will give you, in fact, even much better idea. And if you want to get really, really good idea, then you have to go for 7th degree or 8th degree. That's where even in Bitcoin and stock indexes, you'll have 7 WMMA. I'm not sure you've heard of this or not. Weighted mean average of 25 days, 30 days, 100 days, and so on. But because we're using neural networks directly, any order which is required will be learned by neural network. So we do not have to think about it. But the moment the problem goes outside neural network and you have to think of loss function, the changes in loss function and other things, these problems are going to come in. Because you will be required to write these kind of integrations with the normal things, and you have to integrate it back, right? Because it's not going to be only for images. In future, you will work with sensor data coming in. How do you know the sensor data has deviated? Neural network won't tell you that. That's just taking in the data. So now you can look at the average or the mean of the data coming in. but that will keep on changing continuously, and you'll keep a let's say moving average of last 3 images. So not know suddenly it has gone so dark from the initial stage. To make sure that you do that, you're going to basically have to cover the second order, third order, or maybe take data from the past history also.
Is there any intuition, Rohan, about the second derivative of loss with respect to weights?
Second derivative loss with respect to weights. What intuition are you looking for?
So the first derivative is the gradient itself, right? It helps us understand, how the things are, and we back propagate it essentially to update the weights.
Correct.
But now that you are talking about the second gradients, is there any kind of a view on the second derivative of loss?
Have you heard of Adam compared to S?
Yeah, the optimizer, correct?
Yes.
Yes,
So
for NLP.
all of them are going to use the second derivatives. So we are going to use second derivative also. Not only we need to know the loss has changed, we have to know that loss has changed with respect to the change also. So we are going to use it. Okay.
Okay. Thanks.
Okay. Cool. So this is where we're going to expand the image. But the problem is this will cause checkerboard issue. There's no way we can get out of this problem. And this was first shown in this neural network, where you see the last image, really high quality, but you can see these lines on the front. That's where the checkerboard issue comes in and becomes a problem. Okay. Yes, no?
Yeah.
Yes. Yes.
Now to solve this problem, a new algorithm came out which is called pixel shuffle. Unfortunately, I'm going to explain this only once because this is a complex algorithm to understand. If you don't understand, look at the video back. This algorithm will not help you to do anything unique in future, but this will give you a very good idea of what you can do with the data yourself. Okay, so if you don't understand, don't ask me to explain it again. So I'm literally saying this to make sure that you focus right now and make sure that you understand this at one go. Okay, now what we are going to do is we're going to take our image. Okay, can you see that we have 9 pixels here?
Yes.
Okay. Yes. Now I'm drawing another channel. Let me this time draw the second channel with some other color. How many channels are you looking at right now?
2.
2 channels. What we are going to do in this algorithm, and you might find this really weird to begin with, but that's what we're going to do. I'm going to take the first red pixel, this one, and place it here. It's very similar to the deconvolution process. Then I'm going to take the second pixel and place it here. Then I'm going to take the third pixel and place it here, and then so on. Everyone understands what has happened till now?
Can you fill intermediate values with the other channel?
Yes. And then I'm going to now take what? Green pixel and fill it here. And so on.
So you are
What
mixing
about the
channel.
vertical gaps?
So right now I can't do anything. I can only create 18 pixels out of this, right?
Yeah.
Yeah, so I can't do much. But if I had 4 channels, I could fill the whole thing. Correct?
Yeah.
That's where the number 4 will come very important soon. Okay?
Okay.
Yes, no?
Yes.
Okay. In fact, let's make other channels also. So this is pretty clear.
So it's basically kind of like stretching the data in one direction.
No. That's why I can't be lazy. I have to draw it. So you don't make such conclusions.
You're filling the information from different channels together.
Yes.
Right? Is it not that we are destroying the information that has been extracted and then again reworking on the same thing? Like you separated out the channels, say one is nose, one is ear, one is hair, and all those, and then again.
That's not the problem we're solving here. What is the problem we're solving here? Super resolution.
Yes, but by doing all this mixing up, the actual information itself.
I had the same question because each channel is basically extracted out features, right, from different kernels, and we are basically mixing them here.
Yes, and do you think there's no correlationship between the? Did you notice that I'm picking this pixel and this pixel and this pixel and this pixel together, which happens to be spatially exactly at the same point?
Okay, so one of these channels will not have the feature amplitude.
Yeah. So if this and we're talking about super scaling kind of problem, right? So all the images will have contextual pixel at the back of it. We're not talking about object detection problem. We're talking about super scaling here. So if there was a nose on the backside of that, so all the channels will have a nose contextual data only. We're not talking about object detection here.
So we are doing this sequentially, like kernel by kernel.
Yes. So what we're doing here is, as you can see that we have this 1x1x3 because I'm looking at 3 input channels. I'm using this 1x1x3 and I'm using a lot of 1x1x here. And every time my 1x1 comes in, I'm going to increase my number of channels. I'm going to increase my number of channels. Why? Because the same problem you identified, that I need 4 of them to be able to do something like this. Right? So imagine that I had 3 channels to begin with, RGB. I can't work with them. I'm going to convert them into 12 channels first. So I have a multiple of 4. Are we clear? Or some number to increase the number of channels. Yes, no?
How are we going to do that?
Okay, now let's see what exactly we want to do first. So imagine that I have an image of size 12. I want to convert that image size 12 into what? 24. Let's say this is the problem we're going to solve. Okay.
Okay.
Okay. Now I've taken a bigger number. Anyways, how many pixels I had here? Let's talk only about the red channel because same process we're going to follow on the green and blue also. How many pixels I have here? 12 cross 12 is
44.
44. And how many? 144, and we want to convert this into 24 cross 24. So what is the increase?
4.
4. So I have to now convert this into, I somehow have to add 4 pixels. Okay. So what I'm going to do is I'm going to start at 12 cross 12 cross 12. We are solving the problem of only the red channel right now. So I'm going to start from there. What is the last thing? At 12. No, not 12. Sorry. So I'm going to start at 12 cross 12 cross 3. We are only solving the red channel problem right now. I'm going to use a 1 cross 1 cross 3 cross 12. What will I get?
You get 12 channels.
I'll get 12 cross 12 cross 12. Are we clear?
Yeah.
Okay. Similarly, I will get a 12 cross 12 cross 12 from the green channel for the green channel process. And same I'm going to get for the blue channel also. 12 cross 12 cross 12. Okay. Okay. Then I'm not going to draw the whole thing, but let's draw just the blue part a bit and a green part a bit. And then a red part of it. Now I'm going to pick 1 pixel from the red and arrange it here. Okay. 1 pixel from the green and arrange it here. But I have 12 of them. Okay, 1 second. That's the kind of arrangement we are going to do from each of these channels. It's much better explained in this animation. First look at the animation, then we'll come back here. So first step is I've taken a 5 cross 5 cross 3. Then I've used a 1 cross 1 cross 3 cross 9 here. 1, 2, 3, 4, 5, 6, 7. And I'm going to take a screenshot so it becomes easier for. And then we have this arrangement. Are you getting some idea? Any idea? No idea?
No idea.
No idea. Okay.
7, 8, 9.
We'll follow the animation numbers, so it will become easier. In the animation, what are we starting with?
So these 9 orange blocks are there because we are using 9 filters of size 1 cross 1 cross 3.
Yeah, but we're starting with 5 cross 5 cross 3.
Cross 3, yeah. And convolving it with 1 cross 1 cross 3 into 9.
Yeah, we're convolving it 5 cross 5 cross 3. And then we're convolving this by 1 cross 1 cross 3 cross 9. Correct? What will we get?
5 cross 5 cross 9.
We are going to get 5 cross 5 cross 9. Correct?
Yes.
Everybody?
Yeah.
Okay.
Yeah.
Okay. Now I have to arrange this. I have to draw this. That's why I avoid explaining this. I have to draw these 9 channels. So first channel, second channel, third channel, fourth channel, fifth channel, sixth channel, eighth channel, and ninth channel. All right. Then I'm going to pick first pixel of each of the channels. I'm going to pick this one, 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 and this one. And I'm going to arrange it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Then I'm going to pick the second channel, a second pixel of the same image, but that's going to be the next one from here. Can you see it? This one.
Yes.
I'm going to place it here. Then I'm going to take this next one. I'm going to place it here. Then I'm going to pick the next one, and I'm going to place this here. And the process goes on so on.
So Rohan, how are you arranging this? Is it like
Yes.
channel?
Now let's talk about the arrangement, because that arrangement is everything. Now this first pixel went here. Correct?
Yeah.
Second pixel went here. A gap of 2. If I were to draw this one more time, let me pick red, yellow now. If I were to draw this one more time, we'll have a yellow here and yellow here and yellow here and so on. And the yellow would actually go here, correct? Right? So you can imagine this channel with a dilation of 3.
Yeah.
And that's how the placement is.
Okay, so all the pixels, all the pixels or the pixel 1 from all the channels will be kept adjacent to each other. Then the second pixel from all the channels will be kept adjacent to each other. Then the third, then the fourth, like this, right?
That's correct.
So you are reducing the channels also, number of channels also? Like 4 channels is equal to becoming 1.
9. Here 9 have become 1. Okay. I
Yeah.
got a very simple and fast way of explaining this. So let's do that. Object. So I'm going to create my first channel here, and we have an array of, let's say, 6 cross 6. And I'm going to add a bit of gap in between so we know what we're doing. And then we add one more array. And then This is in the second dimension. This is 1.1, and this is 0 for us, and this is a 6 cross 6 for us. 1, 2, 3, 5, 6. Are we clear? That's the first channel.
Yeah.
Okay. Now SZ.1. I want this to be small. Okay. Now. Okay. Now in the animation we saw how many of them? 9 of them, right? We start with 3, but finally 3 to 9 is clear, right? I don't want to explain that.
Yes, sir.
Yeah, the number of channels increased to 9.
Yes. So this is our second one, and actually. Okay, are we clear till here?
Yes, sir.
Okay, now what we're going to do, we're going to spread this further. So we go back here, and instead of 1.1, I need to spread this to 3, not in that direction. Okay, I need to spread this. Oh, first one first. Okay, I'll just spread this here, and maybe this much. At 3.3 is perfect, I think. And I will spread this also in this direction and make it 3 by 3. Okay. So we're going to place all of these guys here. Now, same thing we're going to do for this also. This becomes our 3 by 3. And this also becomes our 3. And we are going to copy and grab it and place it here. Okay. Is it clear now? What exactly is happening in the process?
Yes, sir.
Yeah.
Okay. And we are doing this right now only for the red channel. Same process we have to do for the blue channel. So how many 1x1s I need actually? Fast.
9.
9 into
9
3,
3 3. 9 is
27.
27.
Yeah, exactly. So how many 1x1s? So let's say we start with 5x5x3. What will be the 1x1s I need?
So 1
Same,
cross
right?
1 cross
9.
3 cross 9.
1 cross 1 cross 3
3
cross
cross
9.
9.
No.
So we need 5 cross 5 cross 9, right?
What are we getting right now? No, we just discussed the channels. Okay, how many channels are required here to just make the red channel?
9.
9 channels.
Okay, how many channels we want to make? R, G, and B, right?
Yeah.
So how many 1x1s we need total?
3.
3. 3 for RGB, and then 9 to 27, right?
27. So we need what? 1x1 cross?
27 total.
27 in total. Are we clear?
Yes.
Do you understand the algorithm now? Let's talk
Uh-huh.
about the use case in a moment, but do you understand the algorithm?
It looks colorful.
Yeah. So what you have made right now is just the red channel. And similarly, we'll have to do the same process exactly for the green channel and then the blue channel. So that means if you're starting from, and if you remember that we started only for 6, right? If I take this out, this is 6 cross 6. So we started from 6 cross 6 cross 3, right? and then we convolved it with the 1 cross 1 cross 3 cross 9 in this specific case, but we would have done it for 27. So keep that in mind. So this I'm going to write as 9 cross 3. I'm going to carry forward this cross 3 everywhere. So that means that I'm going to get a 6 cross 6 cross 6 cross 6 cross 9 cross 3.
9 cross 3.
Okay, so that's where we're going to start. And remember that this 3 is going to be used later on. Then I'm going to only arrange these guys, right? Now, when I arrange them, I'm going to get what? (18 cross 18 cross). Are we clear? Okay, forget this 3. How many pixels are there? 6 cross 6 cross 9, right? So I can write this as 6 cross 6 cross 3 cross 3.
Yeah.
Cross 1, right? Then that means I can write this as 18 cross 18 cross 1.
Yeah.
That's what we've done. Are we clear? I don't want to spend a lot of time on this.
Yes, sir. Yes, sir.
Okay, the reason I still have spent a lot of time on this is what? Why do you think I've spent time on this still? Even after telling you that this is not going to be super useful in future. What I want to take back from this is this particular algorithm might not be super useful for you, but do you understand that you can do something like this? Is this part clear? This is the most important part. That you have the liberty of doing something like this where you can arrange the pixels the way you want, and that will come in handy in future because you may want to mix pixels from multiple different sensors together, multiple different kind of sensors, maybe lidar versus color versus, let's say, a spectrogram versus a radar, and you can actually build a super resolution image out of that data as well. That's why I wanted to cover this. But this kind of rearrangement is possible. People have used it, and you're free to do it whenever you want this in future. All right?
Yeah.
Okay. So this is gone. Now, can you tell me what is wrong with this convolution?
The channel, the kernel itself has 3 channels, or it's a depth of 3?
we are doing like we are merging channels also, and we are reducing also, right?
Isn't that what we do?
We don't merge. We merge channels in 1 cross 1, right? Generally.
How many kernels do we have right now?
We have 1 kernel, right?
1 kernel will give us 1 channel.
Okay, yeah.
So what is wrong with this convolution?
Is something wrong?
There's nothing wrong in this. The only mistake I did was to not color the channels properly of the kernel. So nothing is wrong with this. Okay. But why are we looking at this? We're looking at this because from this now we can come out with something called depth-wise separable convolution, something which is very, very interesting and innovative and sort of started the mobile convolution revolution. Now in depth-wise convolution, we will have 1 kernel with 1 channel for each channel. So what you're going to do here is we have 1 kernel with 3 channels here, right? And we are convolving all the 3 channels together, and then we are getting the output. But in case of depth-wise separable convolution, each of the channel will have its own kernel. Are we clear till now?
Can you explain it again?
Each of the channel will have its own individual kernel, compared to here where we had 1 kernel looking at all the channels together.
So, sir, the kernel will be of size. Let's suppose we have 3 channels. So the kernel will be of size 3 cross 3 cross 3, right? Because we have 3 channels. Just for the sake of example, I'm saying. Suppose
No. 1 second. So let's say we're convolving 5 cross 5 cross 3. In normal convolutions, we have what? 3 cross 3 cross
3 cross 3. So
and
3
then
into one.
12. Let's say
into 12. Yeah.
Right. This is the normal convolution. What we are going to do now is we are going to use a 5 cross 5 cross 1
1.
cross 3,
Cross 12.
right? This is the input now. Right?
So
Then
why
after
3 means 5 cross
have
5?
For each channel, you have a separate kernel. That's why 3.
Acha.
right, you have 3 input channels, right? Or let's look at the image and be consistent with the image. So in the image we had, let's say 7 cross 7 cross 5, right? We have to use a 3 cross 3 cross
5.
1 into 5. No.
3 cross 3 cross
5.
5. This is the old way, right?
Yeah.
The new way. In the new way, what will we have? 7 cross 7 cross
5.
So the
But
kernel size will be okay.
Let's take it step by step. Forget that we had 5 channels. We had only 1 channel. Okay. Okay. Now this will now normal convolution. What do we do? 3 cross 3 cross
1.
1.
1 and cross 1 only. Okay. We have only one of that channel. Okay. Output will be what?
3 cross 3 cross 1.
5 cross 5 cross
5 cross 5 cross
1.
1. Okay. Let's finish this also, and this output will be 5 cross 5 cross
Same.
5.
1.
Oh, into 5.
5.
Why 5? 2. It should be 1.
We did not define.
He didn't specify the number
Huh.
of kernels there.
Channels. Yeah, or filters.
Yeah. So let me write it. Okay, so we start with 7 cross 7 cross, let's say 5. We convolve this by 3 cross 3 cross 5 cross 18. That's going to give us 5 cross 5
5
cross.
cross 5 cross 18.
Okay, so this is the normal one. So this is our normal convolution. Okay, now in depth wise, we are going to start at 7 cross 7 cross
5.
1.
5.
Forget
Okay.
5.
Why 1 is there? That's the
Depth wise, we are going to convolve every channel separately.
Into 3 cross 3 by 1.
so into 5 would come there, right?
I
Somewhere.
will bring the 5 back because people are getting confused. I'm not writing it.
Okay.
Okay, so we'll have 3 cross 3 cross
1.
1.
cross
18.
1.
Why not 18?
We'll come back to that.
Because this kernel is looking only at one channel.
One and giving one output. Okay, and then what is the output right now for this?
5 cross 5 cross 1.
1. Okay. Now we have Control Shift C, 5 such processes. Okay.
Okay.
Each for each depth. So in short, I can write this as cross 5, this as cross 5, and this as cross 5. Yes, no?
Yes.
Are we okay till now? There are 5 operations happening parallelly in the RAM.
Yeah, but they are separate. You are considering them as separate.
Yes, all of them are separate. Okay. Yes, no?
Yes, sir. So one kernel per channel, right? We can so because in normal we have used 18 kernels. Here we have used just one kernel per channel.
The depth wise is not finished yet. It is just half process. Are we clear till now? Okay. What is the output right now? 5 cross 5 cross 5. Correct. Now we're going to use 1 cross 1 cross 5 cross 18, and we are going to get
5 cross 5 cross 18.
So you have reduced the number of parameters. Is this what you have done?
Let's see. So right now, just look at this image and just convince yourself this is what we have done. Let's look at it normally. So we would have done 7 cross 7 cross. We start with 5, and then we were to use a 3 cross 3 cross. Looks like 5 cross 3 outputs, right? This is what we have done. But right now, what we have done is 7 cross 7 cross 1 cross 5. We convolve it with 3 cross 3 cross 1 1 cross 1 cross 5. We got 5 cross 5 cross 5. Then we convolve with 1 cross 1 cross 5 cross 3. That gave us 5 cross 5 cross 3. That's what we did. Correct?
One,
All right.
5 cross 5 cross 5. Okay. This 1 cross 1, I did not understand. And this.
This one cross one. To get to the number of channel expectation,
Okay,
how many channels you wanted, right? Yes, no?
Yeah.
Okay, now let's go back to this and see what we've done. Now I wanted to count the total of parameters here. Three cross 5 cross 18. 810.
Yeah.
So we have 810 parameters here, and let's count the total of parameters used here. Here we have 3 cross 1 cross 5 is 45, plus what do we have? We have 1 cross 5 cross
18.
135.
Oh, so reduce the parameter.
Right, and now let's do it for even bigger number, and let's see what happens. So normally I would have used a 3 cross 3 cross. Let's say I'm getting 32 input channels, and I want to convert that into 64 output channels. Here, in our case, what will we do? 3 cross 3 cross.
64, 3 cross
1
3
cross 1 cross 32.
32.
Right? Plus 1 cross 32 cross.
2 cross 64.
We have a 7.89 times of reduction. Now let's change these numbers and see, do we get some change? Let's say we are going from 164 to 128, and this means this is going to be 64, and this is going to be 64, and this is going to be
128.
We have 8.4 times of reduction now. And instead of this, so let's say we're going to do 56, and this was 128. Then this is also 128, and this is going to be
256.
Yeah, 256 is going to be 128.
128.
8 points. So you on average have 8 times reduction when we use something like depth-wise convolution. All right.
Yes, sir.
Okay. Now Control F, mobile net.
So is there any negative also to this, or just positive?
Yes, let's see. So for example, this is what we covered at the beginning of the session. We observed there's a log relationship between classifier accuracy and the receptive field, which suggests that large receptive fields are necessary for higher level recognition, but with diminishing awards. For example, we note how mobile nets achieve higher recognition performance, even if using a very compact architecture with depth-wise convolution. So this is used in mobile kind of networks where you want to run on mobiles because the amount of RAM required, the computation required is pretty low. And you can increase the receptive field with a small compute footprint. But of course, this is not going to be as good as 3 cross 3, normal 3 cross 3. So, but of course, the computation reduces a lot, and then your performance increases because you have less computation. So your mobile networks are going to be running faster, but the accuracy will drop because now the task of merging and identifying is very difficult for the whole neural network. Are we clear?
Because of less numbers of parameters.
Because of less number of parameters, you're going to be learning less also. But what we have seen is that even though we have reduced the number of parameters by 8 times, the accuracy drop is going to be few percent only. That is startling. That is something which is fascinating, that you do not have to drop your accuracy by 8 times. It's just going to drop by few percentages. Then the question is why the world does not use this in every single algorithm.
But Rohan, like when we were doing this MNIST problem, we dropped the number of parameters to quite a lot, but still the accuracy was very high. Like 99.4% is the accuracy that we were able to achieve with less than 9,000 parameters. So why are we saying that the parameters reduction will drop the accuracy?
See, MNIST is ant, and neural network is literally a hammer. So we are killing an ant with a hammer, and we are talking about how heavy the hammer should be. Right, so MNIST problem is a very, very small problem. The moment our data set becomes something like ImageNet and the whole internet, you need a many number of parameters to be able to solve that. So we are comparing this for not MNIST. In fact, the best neural network model for the same exercise, assignment 4, someone has submitted, has 2,400 parameters. achieving 99.56%. And that person used depth-wise convolution. Right, so it's a small problem, and you can use depth-wise convolution there and actually get a higher accuracy. But moment a problem is complex, you have to go for a higher parameters. And there, when you're going on a mobile and you still want to get it to run, maybe the accuracy is slow, but you still want to run, right? For example, you have seen your face detection algorithm running whenever you open the camera, and you also notice that it's not reliable. Every time it will not detect something, but will detect sometimes, right? There it is actually using depth-wise convolution kind of concept, where you're getting something, but it's not always there. It's better than nothing.
Okay.
Right, and if you see MobileNet V2 and its accuracy, then you're going to see that it's not bad. It's very comparable to MobileNet, ShuffleNet size versus what? Versus, let's say, VGG. Yeah, here we have VGG 138 million parameters, GoogleNet, MobileNet, something like that, 4.2 million parameters, accuracy 71 and 69. So I go back to my question, then why does the world not use this for everything?
We have a lot of compute.
Anything else?
But we don't add a lot of compute, right? You just said.
I think accuracy is the thing that you just mentioned, that accuracy may not be that. So if you are doing a very high precision task, then maybe this is not the right thing to do. Like say counting of the objects. If suppose you miss some certain objects, and that is not desirable for you.
So let's look at this. Okay, so MobileNet here we have at what accuracy? Are we comparing MobileNet? We have MobileNet also. We have NASnet also. Okay, this is a good image. New tab. Let's look at this. This is the latest. Okay, perfect. So we can see that VGG is somewhere around 70s, and MobileNet V1 is at something like here, 78, 68. MobileNet then went on to where's MobileNet V2? Yeah, here we have 74. After that, we have not been able to make a MobileNet kind of architecture which goes beyond 75 and 80. That's where you do need to go back to the real architectures. After that, people have not tried also, because every time any new research paper comes out, they just want to look at NASnet, where it is. In fact, if you go for our papers with code, the current accuracy is going to be pretty high, right? So problem is that everyone is just looking for the highest accuracy possible, not the most optimized one. Are we clear? Right, and if you see right now, the accuracy is going to be pretty high, and this is V1 accuracy, by the way. So we are at here. Yes, 91. This is not a bad number. It's a pretty high number. Okay, but it's a good one. So you need to keep in mind when you're making a small neural network for a small task, it can do wonders. So this is what is happening right now. For each of the channel, we have a separate 3x3 kernel. It's going to give it its own channel. Then we're going to combine these channels and then use a 1x1 to change the number of channels we need. Here, let's say we need just 1 channel or 3 channel output, depending on what you want. All right. Okay. Then we have spatially separable convolution, and this is colored in yellow. The reason this is colored in yellow is because this is not used anymore, but you need to be aware of this. This was used in something called exception, and this is magical. Here, what are you doing? Here, you're convolving on each channel separately, correct?
Yeah.
Okay.
Imagine that you can actually take a slice of the channel across the channels. Imagine that you can take a slice of this like that. So imagine that your kernel, what is the kernel size right now? 3x3x?
3.
What is the size of the kernel right now? 3x3x? 1. What if it can be 3x1x3?
3x1x3.
What if it is 3x1x3?
Kind of extracting a single cube or single cell out of this block.
Yeah, we're extracting a cuboid right now from our images. This was used by Google a lot, and it was a part of the exception and inception network, but then they realized that it's not helping a lot, and then depth-wise was definitely better than this. Now, quickly looking at the calculation of what we will do here. So imagine that Okay. First of all, let's see what are we going to get. So imagine that we have a 7 cross 7 cross 3, and we convolve that by 3 cross 3 cross 3 cross 1. I'm always going to be convolving a 1 right now. Okay, keep that in mind. Let me convolve by okay, let's say normal convolution first. So 3 cross 3 cross 3 cross 5. Output is going to be 5 cross 5 cross 5. Are we clear?
Mm-hmm.
Okay. Now here we have 3 cross 1 cross 3 cross
5.
some number here.
Okay.
And that number is in the quiz, so I'm not going to write that number. Okay. So this is going to give me an output which is going to be what now? 5 cross 7 cross that question mark.
Hmm.
Then I'm going to convolve this by 1 cross 3 cross that question mark cross total number of kernels we needed 5, and that is going to give me
5
5
cross 5 cross 5 cross, yeah.
But Rohan, one thing I do not understand is that, see, generally we take symmetrical things, like a square kind of a thing, so that we can
That's
get
why this is stopped. This is not. This is Google just doing random things in between.
Okay.
And, that's why this little stopped. Okay, giving you the perfect answer. If this is 5, then you're going to get many more number of parameters, and this is not useful at all. So this is not 5. We're going to keep it same. We're going to keep it exactly as the input number of channels to make sure that our total computation is less. Let me quickly show it to you. So if we are not using normal convolution, we have 3 cross 3 cross 3 cross 3 cross 3 cross 5, right? Correct?
Mm-hmm.
For normal convolution, correct?
Mm.
Now we have 3 cross 1 cross
1 cross
3 cross 3 plus 1 cross 3 cross 3 cross 5. You see a reduction of 1.8. But if this was not 3, but this was 5, so this is also going to be 5, then you can see the reduction is not that much. So we are going to keep this as the input number of channels only. Okay, not more on this. Then we have group convolution. Now group convolution is basically a combination of everything. But I wanted to look at this and see what is happening. Generally, what we do is that total number of channels in a kernel should be equal to the total number of channels in the input, correct?
Yes.
But I can decide to have different number of channels in each of the kernel and convolve them separately. So here on the bottom, you can see that I have few channels, and I'm doing 2 groups here basically. So I have 2 groups here, and for each of the group, let's say we split the channels equally. So let's say the total number of channels was 32 in beginning. In the 2 group scenario, how many channels will have in each group? 16. Right? And now I can convolve this by a 3 cross 3, and I can convolve this by a 5 cross 5. I can convolve this by 3 cross 3, and I can convolve this by 3 cross 3. Okay. Now, what I want to show to you is quickly here. So, input resolution is, let's say, 15 cross 15 cross 3, and now we have groups here, and this is the output. We're going to talk about output of each group. Okay, let's say we have one group. The output of each group is going to be
13 into 13 into 3.
Okay, first of all, this cannot be 3. This has to be some big number, so you can multiply and divide. So let's say we have 15 cross 15 cross 16. So Control X and Control V. Okay, so kernel size, if the group size is 1, then we are talking about normal convolution only. So group is going to be 3 cross 3 cross
16.
16, and then cross something, how many we need. Okay, output of each group is going to be what?
So
13 cross 13 in cross
16.
No, not 16. The number of kernels that you.
Number of kernels, right?
Exactly.
But I've taken 1 here, so this one output, right? Okay. Now, if we had 2 groups, then the kernel size needs to be 3 cross 3 cross
8.
8. Output are going to be 13 cross 13 cross
2, right?
Are we clear?
Hmm.
If we had
Output of
then this is going to be 3 cross 3 cross what?
So by the way, output of each group is 1, right?
Four.
13 cross
it should
13,
be
or 1 cross 2.
same output should be there, or total output. Okay,
Yeah,
This is going to be 13 cross 13 cross.
4.
4.
Are we clear?
Yeah.
Okay.
Hmm.
Now we have 2 groups here, right? And we have 4 groups here. Let's talk about this 2 group scenario. Can I convolve one by 3 cross 3 and another by 5 cross 5?
Yes.
Yes,
Can,
because they are independent to each
yeah,
other.
here I can convolve one by 1 cross 1, then other by 3 cross 3, the other by 5 cross 5, the other by 7 cross 7. Or I can do 1 cross 1 and then this 3 cross 3 with a dilation of 1, then 3 cross 3 with a dilation of 2, and then 3 cross 3 with a dilation of 3. Many permutations and combinations are possible. What you need to realize is that this is just a special case of good convolution. What we do is a very special case of good convolution. Can I do this? Can I have 2 groups where the size of the kernels is 3 cross 3 cross 16, and here the size is not defined? This gives me an output of 13 cross 13 cross 1. And here I literally take the input and copy paste it here. That means this needs to have a padding also. So 15 cross 1 or whatever total number of kernels I've used. And this is exactly as my input, 15 cross 16. Right? And imagine that here I had actually used maybe 16 kernels. So, and this output would have been 15 cross 16. Then I can decide to add both of them. If I add both of them, this is going to become 15 cross 16. I can concatenate both of them. In which case, will become 15 cross 32. This here is ResNet.
Why is it 15 cross 15 after one convolution there?
So here you see what is happening. Here we have 15 cross, let's say 3 coming in or 16 coming in. Okay, so we're talking about X. X is defined as 15 cross 16. All right. Then we convolve it in these two by 5 effectively. So I'm just writing 5 cross 16 cross, let's say 16. All right, this is good. And we have done padding also. The output is going to be 15 cross 16.
Okay.
And this X is exact copy of the initial stuff, which is now can be written as 15 cross 16. So now I have 2 options. This plus what you're seeing right now. This plus you're seeing right now can either be element by addition, which makes it ResNet, or it can be concatenation, which makes it inception. Are we clear?
Okay.
Right. So this is also good convolution. So anything you see online is actually good convolution. Here is one more. This is ResNet, so that's fine. Different kind of resonance. So everything you see is a kind of good convolution, and they're going to be just special cases of each other. You can define the total number of channels to be total number group to be 1, and then take a line from sideways called highway connection where no convolution happens. That is also good convolution. So you can become creative, which is where Google went. They went so creative that they designed something like this. What do you see here? 3 cross 3 with stride of 2, 3 cross 3 with a stride of 1, 3 cross 3 with a stride of 2, 1 cross 1 cross 1 cross pool stride. This is max pooling. Look here, we have 3 cross 3, 3 cross 3, 3 cross 3, 3 cross 3, and so on. And we have many weird architecture these guys have come up with. Here you see n cross 1, 1 cross n. What convolution is this?
We can't see. Can you zoom?
Do you see this 1 cross n and n cross 1?
Yeah.
This is this convolution, spatially separable convolution. So there are many variants of convolution architectures possible. Fortunately, finally, everyone has concluded ResNet is the best. So you do not have to go through all of this. So in group convolution, you can have either looking at all the channels or some few channels, or all the channels but have a highway connection also, or a combination of them. You can decide that one group is 3 cross 3, other is 5 cross 5, or you can decide all the groups are 3 cross 3. We have n number of options. But ultimately, this is done to reduce the total number of parameters. Imagine that we're going from 15 cross 15 to 13 cross 13 using a 3 cross 3. So in a normal case, I will have a 3 cross 3 cross, let's say we're going from 32 to 32. Now let's look at group convolution of 2 and how it will have. Here they will have a 3 cross 3 cross. We are split in 2 groups. So I'm looking at 16 channels. I'm going to just create 16 channels, right? And in the second, I'll have 3 cross 3 cross 16 into 16. You see, we have reduced the total number of parameters.
Yeah.
This case is a top case. This case is a bottom case. So people come up with these architectures to reduce the total number of parameters one way or the other. Correct? Yes, no?
Yeah.
Yes, sir.
Okay. One more question. If I had, how many groups I had here?
2.
What if I had 32 groups? If I had 32 groups, okay, first of all, can I write this as into 2 because I had 2 groups? Yes, no?
Yeah.
Yes.
If I had 32, then this will be what?
1 into 32.
1. This will be what? 1. And this will be what? 32.
32.
What convolution is this?
Depth.
This is depth-wise convolution, where the total number of groups is equal to total number of channels, right? And this is depth-wise convolution. So this is also a kind of group convolution. So group convolution is many forms. So don't get confused that we have not covered. Every form is a group convolution or a special case of it, right? This is an example of inception module: 1 cross 1, 3 cross 3, 5 cross 5, 3 cross 3. Max pooling also is also there. You can do 3 cross 3, 5 cross 5, 1 cross 1. In fact, in the next paper, they came out and said that, okay, we now know that 5 cross 5 is actually 2 times 3 cross 3. So the next paper, they had 1 cross 1 followed by 3 cross 3 here, followed by 3 cross 3. So our understanding remains consistent. This is ResNet. This is also kind of group convolution, where we have one branch without kernel, we have one branch with kernel, right? And we can decide to have 1 cross 1, 3 cross 3, 5 cross 5, and 3 cross 3 max pooling. Of course, when you're concatenating them, we have to make sure that the size of the total receptive field is perfect, same. And you can see we have a 3 cross 3 max pooling here. So let's go back to our output resolution problem. What is the output resolution when we are using a 3 cross 3 max pooling with a stride of 1? Formula is going to be input channel size. Let's say that's 7 plus 2 into padding. Let's say we have a padding of 1 minus the kernel size, which is what? 3 here. And if we use a stride of 1 for max pooling, we don't see a change. You have to have a stride of 2 to actually make the change. So max pooling, we're just aggregating the maximum pixels from a nearby region and use it. You might ask a question, why are we doing it? This is again Google trying to do something unique. And in fact, I want you to look at something called NASNet, or in fact ENAS. This is what Google has worked on a lot, and all of the series which are on AI trying to figure out. You can see Jeff Dean already there. All the neural networks which are come out to identify any kind of neural network have come out from Google. Right? All of them work at Google, because Stanford and other papers as well. But all the ENAS and NASNet kind of architecture are funded by Google. And if you ask a neural network to figure out a new kind of architecture, it's going to come out with something like these. Not neat. Yeah, these are kind of convolutions we're going to go 3 by 3 separable, then identity, then separable, and so on. Right, and Google will pick one of them. You can quickly see this is how similar this is to our ImageNet, sorry, Inception network. This is actually Inception. I'm not sure why it's showing that. Yeah, because your neural networks will be driven to identify even slight improve in the performance, and the moment it finds that, Google will come out and publish a research paper. Fortunately, Google stopped, and we are back to transformers. Now, this is also group convolution. This is ResNet here, where 1 cross 3 cross 3. This is called a bottleneck layer. Then we have 1, 3, 1. You can see that instead of 3, you can use a depth-wise convolution also. This is mobile net actually, yeah. So these are mobile net architectures, again by Google, and you can see how complex they are. ShuffleNet, MobileNet, and ShuffleNet I think was by a Chinese company. Anyone remember where ShuffleNet is from? This is, I think, that face, Megaface, what is it called? Megwe. Anyone know about Megwe? Anyone has heard about Megwe?
No.
So let's write outside Megwe and look at news. This is what they do. The large scale, if you have ever heard about large scale stuff happening in China where everyone is tracked, that's Megwe. Blacklists, of course, a blacklist outside, but all the major government level recognition which happens, face recognition kind of problems, is handled by Megwe. It's a very big corporation based out of China and does good work and publishes also. Okay, now to our last topic. We'll be quick on this. This is on data augmentation, or why should we fall in love with this? Now, this is the relationship between the data and the validation accuracy. You can see that as the number of examples in our data increase, our validation accuracy goes up, but the relationship looks like what? Do you think this is a linear relationship?
Yeah, looks linear.
Anyone else?
It's intersecting after some few million examples.
Okay, so whenever you see a graph where on the bottom you have numbers not linear, they're definitely not linear, right? This is 10, 30, 100, and 300. So gap between 10 and 30 and 30 and 100, 100 and 300 is not same. They're 3 times of each other. So this is a log graph, which means that if you have to increase your accuracy, you have to increase your data set exponentially. Are you with me?
Yeah.
That
Okay,
can't
so
happen.
not necessarily parallel, but they are.
Right, so the relationship is logarithmic between the accuracy of a data of a model and the data set required to increase the accuracy. And this is experimentally proved also multiple times. And we cannot have exponentially increasing data set. That's why data augmentation comes into picture. Data augmentation is effective alternate to obtaining valid data because it's similar to your data but not similar. It's slightly rotated, slightly enlarged, slightly oblong, and different stuff. We have many data augmentation policies, but finding the right one is time consuming and it requires a search of the policies also. There's some simple stuff and there are some complex stuff also. If you want to read about this exponential stuff, then you can click on this link and it will take you to paper. Now, the techniques we have already used like dropout, patch normalization, L1 and L2 are already data augmentation strategies. If you think about it, if a particular pixel is black, that can only happen if the input has something in it, right? On the channel number 7, a particular pixel is black. That can only happen if the input has changed.
Yeah.
But we can do it by dropout also. Correct?
Yeah.
If the pixel value is a 0.5 gray, that can happen only because the input has changed. But we can do it by our batch normalization also. So whatever data augmentation strategies we have heard or regularization strategies, they're somewhat in the essence trying to change the input image itself. Same goes for the L1 and L2 also. A particular kernel is forced to become 0, which means the input is not going to multiply with that kernel and output is going to be 0. But it could have been 0 if and only if our input was 0, right? So there are alternate ways of, without changing the image, how do we actually change it locally? But these are local operations. Locally, we're actually changing them. Globally, if we have to change them, then we have to go back to data augmentation, where we can rotate the image, we can scale the image. So what options do we have? We have PDMA, which is actually a term. It's called Poor Man's Data Augmentation Strategies. So I expanded on them and made 2 more called MMDA and RMDA. MMDA is what we are going to be using. This is called Middle Class Man's Data Augmentation Strategies. You'll not find this online. And then we have Rich Man's Data Augmentation Strategy, which we are not going to be using. Are we clear?
Okay, and why are these names like poor man, rich
Poor man started because this is really a poor strategy where you just rotate it, scale it, add noise, and do some random stuff without thinking. That's why this was called poor man's. If you go back and say, I've rotated my data, in the real computer science, AI, deep neural network areas, they're going to say, okay, you're a poor man because you just rotated it or just changed the color bit or done something weird or just added noise. All of this is poor man's strategy. So we're not going to we are going to use them, but that's not going to be what we're going to be dependent on because we have far better strategies than just this. Okay. And by the way, all of this can be done through one single library, and we'll take a look at it. We're going to do something called MMDA, which is our term for middleman's data augmentation strategy. Now we have two beautiful libraries for performing MMDA. We have one called IMG AUG. This works really well with TensorFlow. We're not going to use it. We're going to use something called albumtations. And albumtation has everything you'll ever need for any kind of data augmentation. And it's very beautiful, especially for one specific stuff which I want to focus on. And this is called, do they call it right? No. So we have a term for this. This is called label preserving data augmentation. What is it called?
Label preserving
data augmentation.
Yes, and let's see why are we calling that and why it's very important. Look at the image on the left and look at the image on the right, which is augmented. Look at the labels. The labels have also been augmented. So it has preserved the labels, and that's why it's important. If you do this just randomly, then you'll not be able to basically do something like this.
Sir, but data augmentation, we don't actually, change the actual training examples. We just on the fly, basically, we do all those transformations during the training, right?
That is called
poor man's. Okay.
So if you're doing something like this, where you just rotate it, blur it, add some noise, etc., that's poor man. That's a base minimum anyways expected, sort of kind of thing. So people, in fact, don't even use them anymore. Slight rotation is fine, but making it slightly bigger, adding noise and the stuff is not the way to go. Right? These are the way to go, where we can actually change the image itself in such a way. Now, this can be a proper training data, right? There's nothing wrong in this.
So we are changing our training data because we are changing the labels as well.
Yes. What all we have done here? What are the two things we have done here?
I think we have flipped it, right?
Horizontally flipped it and
crop
and zoomed it, or
yeah, and we have cropped a particular region, right? So this is something which makes our data much more interesting. So we're going to be using albumtation, and this is a new table, and it's pretty fast compared to anything else. This is Keras, this is Salt, this is Augmenter, then this is IMG AUG, and this is Torch Vision below SIMD backend. This one, this is the by default one which is there in PyTorch, and they keep on improving it. But you can see the total number of images I can process per second in albumtation is faster than anywhere else. Right, and this table is much better shown here.
So does it do everything at one, or we have to specify what?
No, you have to specify what you want. It has all of these features, but you have to pick exactly which one do you want. Right, you have horizontal flip, shift, and all. And this is the table I was referring to, and this is the throughput. So it's really good. You can see that for something, a random crop is a very important one. We are going to be using this a lot, and does real good work. 50,000 compared to 163,000. Okay, so
does it have cutout also?
No. So it stops at the basic ones. Then we have to build on top of it. It has cutout implemented, I think. Okay. Now the first important one to understand is called elastic distortion. Now elastic distortion does exactly what it means. It's going to elastically distort your images. Now, where exactly this is going to be useful? I think this is extremely useful in handwriting recognition. So if ever you work on something like this, you can make your handwriting start from someone really good in the class to someone which is written by
a doctor.
Right? So you don't have to go to doctor and figure out a data set, and this will do a really good work in doing something like this. In fact, there's a very beautiful work on the Bengali text someone did, and we can read more about here. And they actually use this whole image augmentation strategy. And you can see that I can't read this, but they took the original data and then elastically distorted it, and of course got really good results. So this is the elastic distortion. So original blur, median Gaussian, motion blur. Then there's original Gaussian multiplicative, cutout, elastic distortions here. Right. So use it. It's going to be really helpful. And this is the paper. Now, then we have cutout. Cutout is the most important image augmentation strategy, something which every research paper challenges and something which has not been beaten for simplicity and accuracy, efficiency. Cutout basically means we are going to cut out a particular part of the image. Now, the way we do it is slightly interesting. So let's take a look at it as in a image. We are going to take our image. Let's say this is the size of the image we have. Then we are going to pad this image, Control Shift and V, and we are going to make our image bigger. We are going to do a padding of 50%. Are we clear? Are you with me?
Yes.
Okay, so this is the padding and this is the original image. So our original image is at the center, and then we are going to take a pad of it. All right. Then we are going to take a cutout region, which is going to be 50% of this image size. So this looks like a 50%. And this is the region which we are going to cut. And we are going to randomly place it anywhere in this whole yellow part now. It can be here, 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 it can be here. Are we good? These are our default parameters.
Yes.
Okay. So this is how this is generated. And now you can see that why do we have this rectangular region cropped? Because we had some area outside as well. Cool. Now, one thing which people do not follow properly, and I insist on it, is that what color do you fill this with? When you cut this region out, what exactly are you going to fill this with?
Here it's gray.
Black.
Okay, the moment you fill with black, your mean and standard deviation for the data set has changed.
So maybe the average values around it.
You are going to fill this with the mean of the data set you have calculated.
Oh, okay.
Okay, so we don't change the effective standard deviation numbers. So that's the gray we are going to be using, and it's there in augmentation. Number of holes, you can decide to go with more than one cut also. This is a default which is there. I do not recommend this. Whenever you are going to be submitting any assignment, I want the number of holes to be equal to 1. I want the max H size and max W size to be 50% of the size of the image. And I want the fill value not to be 0, but equal to what?
Mean of
The data set. Now, always apply equal to false. So there's a probability of 0.5% you're using here. All right. So those are the numbers you're going to use. Now, what is the maximum cut size we can use? 50% as a shared. And you can see some examples here. We are using ResNet and ResNet with cutout. You can see the overall increase in accuracy. Then we have wide ResNet. Then we have wide ResNet plus cutout. You can again see a really good increase in accuracy. And then we have shake equalization, blah, blah, blah.
What is C10, C10 plus, etc.?
Sorry, these are okay. C10 is CIFAR 10. C10 plus is CIFAR 10 plus additional data. C100 is CIFAR 100 and CIFAR 100 plus additional data.
Are these data sets?
These are data sets. So you can cheat, right? Let's say you want to increase your accuracy in CIFAR 10. Why don't you train your network on some other data set, including CIFAR 10, and then prove that you're better on CIFAR 10? That's what people started doing in between. Okay, then we have something called mix-up. Mix-up is extremely difficult to implement and makes our network complicated to write, because finally we have to add a label into lambda and 1 minus lambda. What you're going to do is you're going to take a number between 0 and 1 and take, let's say, 80% of the cat and 20% of the dog, mix them and ask the model to predict 80% of cat and 20% of dog. Extremely hard to do. Your training accuracy is going to be very low. Test accuracy is going to be excellent.
Is it doable in augmentation?
It's not doable in implementation. You have to change your code. You have to do a lot of stuff. That's why it's not used. Complex also, and does not beat our friend called
Middleman's augmentation. Cutout. Okay. So, but in session second, I guess the quiz question had this how this cutout strategy is going to affect the accuracy, and the answer was either the accuracy will be reduced by 50% or accuracy will be increased. So I read a paper and I answered that accuracy will be increased, but the correct answer was like the solution said that it is 50%.
Yeah, because the question is different there. The question was related to the memory of the tensor you were using. The way you will implement cutout in that question was that every time you're going to leave the black patch behind.
Acha. I exactly don't remember the question,
Yeah,
but yeah.
I remember the question because I've discussed that in older EVAs. What the question was that you're doing this and then we are adding a cutout inside that. But unfortunately, you were saving this. If you save this, what will happen finally?
By saving, you mean?
We are changing the data.
Yeah, you are saving the data in that question. You're using a particular tensor where it's mapped with a numpy, and you were changing a numpy and you're sending it here. And slowly you were just filling the whole image with black. Now, if you have two classes, what's the accuracy? 50%.
Acha. Okay.
The code was written in such a way. If you have not identified that, you can go back and check.
Hmm.
Okay, then we have mix-up, as I shared, not used a lot. Then we have recap. Again, a very interesting concept. We take 4 parts of the image, and now we have to predict 4 classes with the same accuracy. So if you have used 60% of this, I have to predict airplane with 0.6. I have to predict penguin with 0.2. I have to predict dandelion with 0.1, and I have to predict ship with 0.1.
So where is mix-up and this one used?
Not used. I'm telling you, it's like Relu, Selu, Kelu, Pelu, and other strategies. I just want you to be aware of this. The only one you're going to be using is our cutout. These are other strategies which are available, but not used at all. And here you can see comparison. We have a dropout, then we have cutout, we have random erasing, then we have mix-up, and then we have recap. Okay, now let's look at cutout. Cutout goes from 3.08 to plus minus 0.16. For Cepha 100 goes to 18.41 and plus minus 0.27. Now let's look at recap, the one we just saw, or the mix-up. Mix-up is very close, 3.02 compared to 3.08. And then we have 18.41 and 17.62 and then 17.22. The amount of effort requires to get recap and mix-up up is not worth the change in the accuracy. We're talking about the top 3% error going to 3.28%. So unless you are applying for a competition, then it does not make sense.
But the stability is more, say for example, you are varying from 3.08 plus minus 6.60.
Yeah, look at Cepha 100. Cepha 10 is not. Okay, and this is their paper, they're doing it. After that, the other every single other state of art paper has just used cutout. No one has used random erasing or mix up or recap. See, this is how I understand the paper is important or not. The author of the recap does not use recap in the next paper, goes back to cutout. What should I think? Right now, these are the image augmentation strategies which have come in. So what we saw here was till 2018 November, and after that we have sample pairing, we have mix-up, we have BC learning, we have cut mix, we have mosaic, we have aug mix, and plasm, blah 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 blah. But the only one people end up using is cutout. Now something interesting came in patch Gaussian. In patch Gaussian, we do cutout kind of stuff, but we don't cut out. In that cut out region, we just add some random noise, right? We add a Gaussian noise in that particular part. This I was hoping actually going to take over the cutout part, but has not done that. People are still using cutout. Then we have RMDS. RMDS stands for Rich Man's Data Augmentation Strategy. In Rich Man's Data Augmentation Strategy, we apply the full reinforcement learning from Google. This is the Google one. They applied this augmentation strategy for 15,000 GPU hours to figure out the best augmentation strategy. 5,000 hours to get the augmentation strategy for Cepha. Cepha you can train under a minute. That's why this is Rich Man's augmentation strategy. And they figured out every single possible combination of what change, what's rotation, what filter, what posterize, etc., and they'll figure out a correct strategy for that. Right? Not worth our time wasting. And then how can you beat this kind of money spending? You can do something called population-based strategy, where for every epoch, from 0 to 12 epoch, you have something else, from 12 to 34 epoch, you have something else, and so on. And their logic is that as your network starts learning, earlier we're learning just edges and gradients, then we're learning textures and patterns, then we're learning part of objects, and then we're learning objects. Our strategies should change, which affect edges and gradients, and then textures and patterns and part of objects. So this is like Middle East doing AI. They have to have this kind of money to test it out for everyone. Next time you train the same model, you would need the same data augmentation strategy. Are we clear?
Yeah, but how are we going to implement this layer wise? Because all this thing will happen layer wise, right?
Layer,
Step by step.
no. The logic is layer wise. You're not applying layer wise. You're applying on the image only.
Okay.
But this is what you're going to be doing. This many times cut out and translate X and translate Y and so on and so on. I find this very stupid approach. And of course, not used in any other state of art these days. Okay, so we can have a lot of strategies on how we want to actually train, but the problem is that it can actually do a reverse thing also. Possible that you apply everything, thinking everything's going in your direction, but look at this example. We do not apply any augmentation. We get our mean accuracy is, let's say, 45, so we are at that part. But the moment you apply WD or WD, I don't know, or weight decay, and then flip and weight decay and flip and carbon weight decay, our accuracy actually is reducing. So applying image augmentation strategy can reduce our accuracy also. We are doing flip here, but if you apply it properly as well, we can actually increase it. Now we are getting 23.5. We apply cutout and increase, and we cut out and huge data and increase further. So this example is taken from an autonomous driving dataset. In autonomous driving dataset, if you flip the data, suddenly you can't drive, right? All the traffic lights are going to be on the left or right, depending on the country, and you have just flipped it. So you have to be careful on where you applied. Now, here's a comprehensive survey came like last month, and this talks about every single data augmentation strategy you might be interested in, but completely up to you. You just need to stick to our cutout. Now, as it is loading, let me explain the assignment 6, which we spoke about in the last session as well. Now, you're going to run this network. When you click on this, it's going to open the link. Fix the network above. You're going to change the network, which I've defined here, to make it look like this. This is C1, C2, C3, C4, and output. Okay, there's no max pooling. You're not allowed to use max pooling, but you have three cross-3 layers with a stride of two instead. So instead of max pooling, I want you to use a 3x3 with a stride of 2. Are we clear on the first point? Okay, so no max pooling. You have 4 blocks: C1 block, C2 block, C3 block, and C4 blocks, followed by output. You're not going to apply any max pooling. Instead of max pooling, you're going to apply a 3x3 with a stride of 2. You can figure out if you want to use dilated kernels also, right? You can use a dilated kernels instead of max pooling or strided convolutions. And if you can figure out how to use dilated kernels instead of max pooling, then you have 200 points extra for that. Your total receptive field for the network must be more than 44. One of the layer must be depth-wise separable convolution. One of the layer must use dilated convolution. We have discussed where do we use it. You are supposed to use a gap. And after gap, you're going to add a fully connected layer to target a number of classes. This is optional, so you can also use a 1x1, or you can actually start with a gap at a total number of channels where it is actually equal to number of classes. You're supposed to use the augmentation library. You're going to apply a horizontal flip. You're going to apply shift, scale, and rotate. You're going to apply coarse dropout, which is similar to cutout. It is actually cutout, where you're going to, we saw that, right? Where max hole is 1, maximum height of the cutout is 16, and then max width is not 1, 16. Then minimum hole is 1, minimum height is 16, minimum width is 1. Why I've written this multiple times? Okay, you get it basically. The same cutout code we saw above. You're supposed to get 85% accuracy in as many epochs as you want. And when you look at this code, this is the first time I think you're going to be working with Cephar. Till now, you have been working on MNIST. The first time, I believe you're going to be. You worked on Cephar already?
No.
Not yet, right? This is the first time. So this is going to be slightly challenging because 84 is a tough number to achieve. But if you just apply this as I explained, you are going to get 85 easily. Moment you do not stick to this architecture, you're going to get something which is pretty bad. Right now, you're supposed to upload to GitHub. You're supposed to attempt our assignment 6 solution page. And these are the questions which I've asked there. Copy paste your model, copy paste the output of torch summary. So I need to know how many parameters you have. Copy paste the code where you implemented augmentation, copy paste your training log, and share the link to your README file.
Rohan, this point number 5 says one of the layers must use dilated convolution.
Yes.
Is it not the same as what you are asking for as a bonus question? If you can figure out how to use the dilated convolution.
Correct. You can use, if you do this, you don't have to do this.
Okay.
Sorry, I didn't get that. So optional is compulsory?
It looks to me.
No, man. 1 second. What is this point on? Max pooling. Why are you confusing with this?
No, you are saying that C1, C2, C3, C4.
No, it's for the second one. The other guy was asking. Who's the other guy? Rohit?
No, I'm saying that point number 5. See, you are saying that your architecture should have C1, so 4 convolution layers, right?
5 is the 5 compulsory?
Yes, it is compulsory, right?
Is this compulsory? No. But if you implement this, then you are already solving 5.
Yeah, that is what my confusion was actually. that you are anyway asking us to use the dilated convolution. So,
But dilated convolution is not max pooling, correct?
okay, you are saying instead of max pooling. Okay, fine. All right. Okay.
Okay, sir. So this albumtation, when we use, we don't have to use that transpose dot compose. Sorry, the transforms dot compose.
No.
Mm-mm.
You said you will be sharing a reference repository for the code structure.
Yes, I think I will add that as a link. Okay, and remember that as we discussed in the last session, your assignment must have this time a model file separate, the training code separate, and then augmentation code separate, etc. So refer to the assignment 5 to figure out exactly how we have to write the code here. And if it is not, then please expect heavy cuts this time. It's more dependent on how you're writing code because the network is already given.
One question, Rohan, here. So in albummentation library, right? So we have to implement it from scratch, or it will be a part of PyTorch?
Part of PyTorch. You just import it, right?
Okay.
Install, transform.
Oh, okay.
This is going to be part of your data loader or just before you send it to your data loader.
Mm-hmm.
Okay, all of these paper also cite that, and if you want, you can go to one of these paper and look at the code, and you get a lot of examples of how to use albumtation. All right, so we end our session here. I'm here if you have any questions, and see you next Saturday. And sorry for not being on the top of my performance today.
Thank
So
you, Ron. Good to see you.